All right, welcome everyone to the on choreographic. Thank you. I'm an assistant professor at UC Santa Cruz, and handed to Coach Vera and Marco, who are going to introduce our keynote speaker.
To open with an anecdote, very fantastic for me. And one of the reviews rejected said choreography is only on ballet and theater. So I don't want to have that anymore. Very the Mac, you need to remember the tone setting. This and please do that. Also, if you can national section, so you can go to your piece of logistics. Last point, tomorrow about how to get information about where to have it and the I think why this event? Well, we thought the time was right to organize this. There have been very interesting works in major venues the last years, and many some breakthroughs, actually moving choreographic programming beyond the theory community to the of programming. So many felt that there was time for having these events, something to start catalyzing the community. This is mainly the main objective of and also, as we're seeing, I mean, every event needs to start with some we have quite some diversity in terms of affiliations and quite a number of person are just citing as one. So it was, I think, a way of marking there are many groups that work on choreographic programming and bring them together. There is an official PLDI. We're organizing the evening at Bruin Street. Half an hour by feet from here. We are going to walking bus. Just follow me after the session. Otherwise, if you don't want to talk, there are a couple of stops you can get there with the M1 and then dinner usually is very early compared to other countries, so after a stay. But let me jump to the first minute and start today's program. Start with Professor. I think he needs a lot of introduction, but there is anyway. The professor at the University of New York is also head of the largest group working on programming. Several papers, topic, and develop implementation of programming. And so idea of university grant with a project on choreographic programming. So with the first person to kickstart this and I leave the
introduction. I'm Harold. Choreographic programming, what it is, why like holder. I'm gonna about why I think we need the background for systems. We have multiple things happening at the same time. complicated different solutions. What we are interested in is understanding the a few weeks ago, story. A research session was out for a social lunch. In is a big robotic program was being served by robots. When we had the human there explain the rule to us, and he told us, please don't order the food at the table, because if you do, then there's not going to be enough space at the table. Very reasonable advice. We had all intentions of following it. Tablet could use to order food. It's all you need. It was so simple. You just and robot just too much for some of us. But it was much for some. They think compulsive rapid tap disorder. Both managed to keep up with it. And so food was coming, everything was right. But we realized the road is me through exactly this. What do you think the other robot replied? Right. We were witnessing a deadlock. Obviously, nobody programmed, or at least nobody programmed correctly, this particular, right? Displayed by the sad face of the robot. Which to the code probably very complicated. So this is very toy example for a single sound. This is W where the client would like to look at, and an authenticator process A. So the client wants to log in through the authenticator process at the web. Explain the code. It's very simple code. It's a toy example, as I said, but we all know that predicting the behavior of concurrent code is pretty complicated. So I don't want to waste a lot of time doing that. And it's complicated because it starts looking like this very easily. You have to start matching which messages are going to be consumed by which other processes at which point in time, and then you follow the internal control flow of each program, and then what this triggers, which then gets received by another process, and so on and so forth. Okay? Now, this thing, which looks circular almost, I would say, but it's not. It's actually very, very simple, right? And the aim of choreographic programming, if you like, put very simply, is that what is simple should also look simple. If you have simple communication behavior that you want to implement, then your program should express it in a very simple way. Some of you might be familiar with this principle, you know, keep it simple, stupid, right? But I think what we are building as a community in choreographic programming is even better, because a lot of people are aiming at elegance in their papers and the abstractions they're building. So I'm going to upgrade it for the purpose of this talk to the chef's kiss principle, if you like, which I'm going to depict like this in the slides. We are going to cook a lot of eggs. So even before choreographic programming, people have been writing choreographies. They're just not programs, right? But when you are interested in specifying or documenting what kind of communications you should have, well, people have been using for many years message sequence art, sequence diagrams, notations inspired by workflows and other graphical notations like automata. Most of the time, it's usually natural language that people express choreographies, but unfortunately, I suspect the vast majority of cases, choreographies are just in the heads of developers, which are trying to form this puzzle across all these programs that they're coding. Because it's a bit in the way, you know. Once you have written a choreography that is just documentation or a specification, it's an additional artifact that you have to make. You haven't coded anything yet. We know this is a bit of a fool's errand. We have overwhelming anecdotal and empirical evidence that even expert programmers make a lot of mistakes very easily when they code concurrent systems. So this doesn't work. Dark times. Where do we look for inspiration? Well, choreographic programming starts from the premise that if we accept that communication is so important to the programming of concurrent and distributed systems, then we should make an abstraction for it and represent it in a manifest way in our programs. Let me draw a parallel with functional programming. If we accept that functions, the function abstraction, so defining a function and calling a function, it's so important to programming, then what would you rather have? A low-level language where then you have to prove manually or verify somehow that, yes, this piece of code is indeed the function definition, and yes, this piece of code actually calls the function? Or would you rather program in a functional programming language that actually gives you syntax for defining a function and calling a function, call it a day, literally? The same we are trying to do for choreographies and expressing emerging behavior. The inspiration coincidentally comes from a notation that is very familiar to people doing a functional programming, right? But this is not the function type. It's not logical implication. It's a notation to express movement of data from a participant A to participant B, which started from the security protocol community. Actually, I'm going to argue later in the talk, it started even before. To avoid any confusion, although I am going to show you that it's actually intimately linked to what you're used to in logic and functional programming later on, I'm going to write for the names of the participants lowercase p's and q's because they are actually process identifiers. So I'm going to read this as the process P communicates something to the process Q. How do we use it? And this is what you typically do in a choreographic programming language. I'm going to use a simple imperative one. I'm going to rewrite the previous example, the single sign-on example we had. So you use it like this. You write, the client C sends some credentials. Credentials is a local variable at the client to the authenticator process A, which stores the credentials that it receives in its local variable X. Then A makes a choice. It reads like a normal programming language, but computation is located, and you have this communication abstraction up there. So if the authenticator process thinks that the credentials are valid, then it communicates the decision OK to the web service, and the web service generates a session token and communicates it to the client C. Otherwise, the authenticator tells the web service the credentials are not valid, and no token is sent to the client. The idea in choreographic programming is that once you have a choreography like that, a program for your entire system, or at least for a part of your system, then you run it through a compiler which generates the code for each participant. And this is exactly the same code I showed you before for the participants, for the three processes. What is the key difference? The key difference is that what was very complicated to look at now looks simple, right? These are exactly the same two flows represented in traditional distributed programming or in a choreography. In the choreography, you can clearly see that first we have the communication from C to A, then A makes a choice. If the choice is OK, then the web service releases a token, right? It takes a moment to see this in the choreography. It takes much longer to see it in the concurrent program. So we're following our principle. All right, one of the key properties you want to establish when you do choreographic programming, and choreographic programming is not just limited all the time to just compiling code. There are many other interesting aspects that I'm going to talk about later, but in the typical incarnation of choreographic programming, you have this compiler. What do you want as a property? You want the compiler to be correct. It's normally established by modeling the choreography language, the process language, and then you show some operational correspondence. One of the most typical properties that you get for free out of the correct compiler is deadlock freedom, which Marco and I here elicited in this paper around 11 years ago. So the idea is that since in a choreography, at least in a language like this, you do not write send and receive actions separately, but you only have the communication abstraction where basically you express the entire thing atomically, that C sends and A receives, you can never mismatch. It's syntactically disallowed to mismatch send or receive actions. Right? So the choreography can always progress, and by correctness of the compiler, the system can always progress. Right? And the fact that you get this for free without even needing a type system for simple choreographic language is a staple of the paradigm. How do you use choreographic programming? Well, here are a few examples. There are more, but these are the main ones. You can write an application as a choreography, compile it, and run it. You can get skeleton code, so you project some code. The projection is just another way, choreographic programming lingo, or choreography lingo in general, for saying compile, typically, because you project the choreography on a specific process. So you compile the choreography to a process, then you get the communication behavior, but you can add details later on. And then you can use the usual method from round-trip software engineering to keep the two representations in sync, choreography and the processes. Or lately, and this has been getting a lot of traction in the past 4 years, I would say, we have choreographies as libraries. So the idea is that you wrap the code you get out of a choreography, and there are principled ways to do this, right? In functions or methods. And for example, here this says that given some credentials, you get an authentication result. You get a method that you can invoke at the client, right, from the choreography. And then you can use this library to code an application that uses it to participate correctly in a protocol. Now, choreographic programming has many phases. I've just shown you one. I can't show you all of them in detail. It would take far too long. But I thought of making a little timeline because it's important to be aware of where they come from and where we are going, in a sense. It starts in 1978, when these two people published a very important paper. Does anybody know who they are? Answer only if you know both. Does anybody recognize them? Somebody needs a security course. Almost. Nope. Yes. And then the other is? Yes, exactly. It's Needham and Schroeder, the authors of the very famous Needham-Schroeder protocols. Now, Needham and Schroeder, they published the first paper where this notation has been used. The A arrow M colon M, meaning A communicates to B the message M, right? They use it like this to describe a protocol for secure authentication that they want to propose. I was very, very curious about where they got the idea from. And then to try and figure it out, I read their paper, and all the papers decided, but some papers are not available online, so it was very hard to do. So at some point, I just bit the bullet, and I wrote to Mike Schroeder, right? Who, by the way, also has one of the coolest profile pictures. Anyway, Mike was very kind. He replied very, very quickly, and he told me that he was quite sure that that paper was the first one where they, with the notation for encrypting messages by using a superscript notation, like this one. But about this notation, the arrow notation, he wasn't quite sure. So he suggested, because this is such, he wrote, it is an obvious way to present such protocols, of course. So he suggested that I contact his PhD advisor, Jerry Salter at MIT. And I did. I was on a kind of, investigative journalism frenzy. So I wrote to Jerry Salter, and Jerry replied, saying something interesting. So first of all, he checked all the papers I couldn't access online. He actually had them, and they do not present that syntax. And second thing he said, I have a foggy recollection that people were using this notation already in discussions for early internet protocols in the 70s, right? That's where my investigation stopped. I talked to many other people. I haven't figured out exactly where it comes from yet. But many people even don't care, because Jerry agreed, and many other people that I talked to agreed, that, yeah, it is an obvious way of expressing what's going on, right? Now, as a language designer, when they hear obvious, self-evident, clear, enough times, I think of this. We are following the principle. So that's what started it all, in a sense. Another landmark, I'm going to jump forward to 2005. Okay, it's a big jump, lots of stuff happened. This is a very incomplete timeline. People developed all sorts of formal methods to reason about concurrent systems, some very successful. But what is special about 2005 is that it is a sort of reminder and representative event, because the W3C, the World Wide Web Consortium, they published the choreography description language. This is a choreography language for specifying, describing the expected interactions of a system of web services. Now, I'm not so interested in the language per se, which was, by the way, incredibly innovative for the times. This being the 2000s, everything had to be done in XML, you know. So this is how our wonderful, simple primitive looked like. Okay, this is the XML of P sends X to Q, which receives it in Y through the operation by over a session channel K. But if you pay attention, I said session channel, there's a notion of a channel. There's a notion of operation. I mean, these people knew what they were doing. Because at the time, for the past year, I mean, in the 2000s, it was a remarkable decade of interaction between the web services community and the community of concurrency theory. And especially the community of process calculus, like the pi calculus and so on and so forth. They love making syntax for expressing and studying concurrent behavior. Marco suggested to me, maybe even too much sometimes. So lots of models and semantics of choreographic languages, which were not yet choreographic programming, but without them, I'm almost sure we wouldn't have this paradigm today. We got that, and also the very famous multi-party session types method out of these studies. So that's why I put it there. It's a bit of a good reminder of why having different communities interact can bring good things sometimes. In 2013, jumping ahead, I proposed in my PhD thesis that we have a paradigm, actually, a programming paradigm that merits consideration. We should really take it in itself as an interesting thing and study it. I did it because of a few things, of a few observations. I'm just going to give some representative examples. One is that together with Marco, not only did we discover that you have this very interesting liveness property for free, but also the abstraction comes with interesting laws. And one very interesting law is the law of independent communications. If you have two communications in sequence, P1 to Q1, P2 to Q2, so independent processes, completely parallel, since P1, Q1, P2, and Q2 are all in parallel, they can communicate in the order they want. So if you have, this is equivalent to swapping the two communications, because we can predict the order in which they will happen. It's an example of out-of-order execution at the choreographic level. When independent processes do independent communications, you can do them in any order. This law comes from the semantics of parallel execution in process calculus. So it doesn't just pop out of thin air. We didn't just make it up. Well, we did formulate it. We made up the formulation. The semantics of time process. Another reason is that I meant to implement choreographic programming. I think it was a bit like the right place at the right time. The theory of choreography at the time was heavily based on, so it was projected to set thieves, and was I developed a programming language which was so very easy compilation in a sense, to focus on really hard problems, which was how to model channels at the time. But it was nice because we went away from lots of theories, and get executable for architecture. So a big jump. Another and final reason I'm going to present for this is that we found a deep link to logic. We knew at the time, because of the proofs as processes agenda between pi calculus and linear logic, the proofs in linear logic correspond to processes in a simplified version of the pi calculus. Propositions correspond to session types for these processes, and that if you follow the process of cut elimination of a proof, you get to see the communications enacted by the processes that correspond to that proof, by the process that corresponds to that proof. But if choreographies are syntactic descriptions of communications, then they should have a place in here. And we did find that place. If you follow the process of cut elimination of a proof, well, that is exactly expressible as a choreography, syntactically. So choreographies, they give you a syntax for expressing a process of cut elimination. And what's better is that we got two things. One is a syntax for pi calculus-like choreographies. This is P communicates to Q over channel X and new channel Y. And we got a confirmation that our law is there also in linear logic. One of the most interesting features of linear logic, some say the most interesting feature, but I'm not going to push there, is that when you do cut elimination, some cuts can be performed independently. They are concurrent, in a sense, right? And we could see that. We could see that when you can perform a cut reduction, basically our communication abstraction, it corresponds to a cut reduction that you have to do, and you will be able to do. When you have two communications that are independent, so two independent cut reductions that you can perform them in any order. Exactly the same law. And that's why I thought that we should give the paradigm a name and we should start studying it for real. Another jump, 2020. Together with Saverio and Marco, we end a struggle, I would say, of how long? 3 years of development, something like that. It was a pretty long road. But we managed to finish Coral, an object-oriented choreographic language. This is the first choreographic programming language integrated with a mainstream paradigm, if you like. In this language, what we did was take in Java, because we wanted to prove that you can really use choreographic programming in the real world. And we extended Java in a very simple way. You annotate a data type with the process it is located at. So this method now reads, given some credentials at the process C, you get back an authentication result at the web service. Now we can express this kind of stuff with a very simple addition. Well, if I can express that, you can express this. This is a communication method. Given data of type T at P, it returns data of type T at Q, right? So we can reconstruct in object orientation the communication abstraction. We don't have to add it as a completely foreign thing. It just comes out naturally of this extension. And then you can write choreographies like this. This is like you have a number 42 at P, you communicate it, and now you have the number at Q. And you can write choreographies like this. I'm not going to go into the details of Coral. There's a presentation at PLDI on Wednesday, if you're interested, held by Marco and Saverio. But what Coral really contributed is that you can use it. It's a single language for any application of choreographic programming known so far. Well, the last one, I think it started with Coral, arguably, because you have this principled way of getting the types for the libraries from the choreographic types. Oops. And and it solves this very important problem of programming in the large. We didn't know how to program in the large with choreographies yet because we didn't know how to wrap them and encapsulate them. And this is the language that introduced that. Now, when we saw that this programming in the large was important, that the choral data types were so powerful, we started getting interested in, well, can we really understand the foundations of this? This is in parallel with the work that Andrew did together with Deepak Garg. We had basically an intention of investigating how do we do the same to lambda calculus to understand really the essence of this. And the idea is very simple. It actually scaled very well, or downscaled, if you like, from object orientation to lambda calculus. You annotate types with processes, and then you can have primitives like this. Come from P to Q, give me some data of type T at P, and I give you data of type T at Q. This is the communication primitive in lambda calculus. You just add it as an axiom to the semantics and type system that whatever data you give it, it returns the same data on the other side. Then you can write choreographies like this. You start with a number at a process, 42 at P. You communicate it to Q, so now you have it at Q. You apply a local function at Q that transforms this number into something else, and then you forward the result to R. This is more or less how we program in choral as well. Another landmark was Haskell, developed by Lindsay's group and Gan and Shun. Do we have Shun? Hello, Shun. Why is this so interesting? It's the first embedded choreographic programming language. It's the first language where people did not have to develop an entire separate compiler toolchain. They just took Haskell and made an embedded domain-specific language for expressing choreographies. And it integrates with the rest of Haskell, right? The communication primitive looks like this. P communicates the expression E to Q, so it looks very much like the primitive we're used to. And you can use the Haskell type system to track that everything is at the right location. Then what you do is that once you have formed a term that is a choreography, you just pass it to a function that they have developed that basically interprets it from the point of view of a process that you tell it, right? So it's a bit like the rest, but interpreted at runtime, and you get this very nice embedded DSL. The idea apparently scales because right away they apply the same idea to Rust, and we are getting more to come. And I know that today we are getting to see at least 2 other shapes of the choreographic abstraction, maybe more. I know that there's one for the Lispy lovers, and there's one where you don't even see the communication because you just infer all of them. Data just falls magically into place. What do all these phases have in common? Well, there's a principle of locality. Data in computation is located somewhere. There's an objective viewpoint. You look at all the processes you have from above. And there's the interaction abstraction with its laws. So these are some of the key features, perhaps the key features of choreographic programming languages. Now, since we are at the choreographic programming workshop, I thought of reporting on some terminology. There are a lot of interesting problems, a lot of interesting theoretical aspects of choreographic programming and choreographies in general. These are particularly interesting. I call them the translational questions. So when you go from choreographies to processes, there are 2 questions, those on the left. One is called realizability. This is standard terminology also from previous works on choreographies from long ago. So given a choreography, does there exist an implementation of it in terms of processes? To give you an idea of why this might not be the case for all choreographies, consider this one. Here I have a process A that makes a choice, and then if the choice is true, for example, another process, a web service, needs to communicate a token to the client. Otherwise, we communicate something else. This is not realizable because that web service doesn't know what to do. The choice is made by another process, A, so the information about the choice lives there. We say we have a problem with knowledge of choice. I'm going to show you later how to fix that. A stronger question is that of projectability. it's the computational instantiation of realizability. So it doesn't just ask, given a choreography, is there an implementation? It asks you to compute it. Can you compute an implementation of this choreography? Of course, projectability is strictly harder than realizability. Here you need to provide a mechanical answer, right? So you need to give me a compiler, for example, that will do it. In between all of these questions, there's an interesting fix, the one that I promised you for realizability, which is called amendment. Amendment is a transformation of a choreography. You give it an unprojectable or maybe unrealizable choreography, and it's an automatic transformation that returns a projectable one. So for example, amendment would realize that this doesn't work because there's some missing information from A to WS, and inject the necessary communications, as in the example I had before. So there are very sophisticated methods to do this automatically. Going the other direction, from processes to choreographies, the expressivity question, which I'm just dubbing, by the way, people have not really thought about that a lot. They mostly mention extraction, but I thought it nice to give the same symmetric view on all of this. Given a process or an implementation, can we write a choreography that describes it, right? This is an extremely interesting question. I'm going to talk about it a bit more later. It's extremely interesting because, for example, well, choreographic languages are usually deadlock-free. So, of course, there are processes you cannot express. But are they interesting at all? We don't know. The computational equivalent. So, given a system of processes, can we compute a choreography that describes it? And here there's a stream of papers, and people have been very successful at it, at least for processes without non-determinism. But still, processes with recursion, there are very strong results about. So if you want to get into semantics of choreographies, I had the terrible idea of writing a book so that people could tell me all I get wrong. But I really tried to be friendly to beginners. Maybe that's why I get so many people telling me about typos, especially students. It follows the structural operational semantics approach by Plotkin. More on that later. And I tried to distill from all previous work why compilers work thanks to very strong algebraic properties in theory of projection. Okay? Now, why am I following the semantics approach? Because all we do normally in choreographic programming papers, at least about the theory of it, is proving these operational correspondence results, right? And essentially what we're proving are bisimilarity results between choreographies and the code we compile out of them. And if you follow the methods in the book, you will basically get a bisimilarity. You just apply the proof in there, and you get a bisimulation. So if you want to get into these kind of questions, the laws of abstraction, of the interaction abstraction, and so on and so forth, I would also really recommend reading Davide Sangiorgi's excellent book on bisimulation and coinduction. Now for something entirely different. So I've been talking about why we need choreographies from a technical viewpoint. But a few years ago, I was contacted by a few art curators. Our university is wonderfully covering many, many disciplines. And I was contacted by these art curators to make an art exhibition about choreographic programming. I bet you don't hear this often in talks. So I thought it was a terrific idea. Let's do it. I had no idea what I was jumping into, right? And Marco and Saverio kindly accepted to help. What did we do? We were having workshops with artists, some very well-established artists and art curators with a lot of expertise and experience, and tried to tell them about choreographic programming, what it is its essence, and so on and so forth. The artists went crazy with it. We had choreographies of fiber optics where you had particles of light interacting with each other and forming different patterns. We had computers talking to each other. We had a plant in a feedback loop with a screen, and they could communicate with each other. The plant could change the color of the screen. And we had a giantography of a choreography that I tried to explain to the public, right? But the idea is that people really liked this, intuition of being able to talk about how things interact. This is not so far from what artists do, after all. We had a real choreographer, like somebody who actually does it in art as a full-time job. And she designed a choreography for citizens. So you come in as the public, you get some headphones, and it gives you the projection for you, essentially, of what you're supposed to do. There's concurrency in it. There's orderly, orderly structures. And in the end, they all join to see what the heck they have realized together, right? Which was not evident until that point, to elicit the difference between your local behavior and the global emergent behavior that you get. You can see it. It's upcoming now. It's been running for a while. It's coming to Sweden, Denmark, and Germany soon. Now, at the event, long story short, we had this discussion with the public. And what really struck me is that from high school students to senior citizens, they were really engaging with this idea of understanding a bit more what was happening between computers communicating with each other. And in particular, they wanted to know, can we use these methods to understand how our data is used on the internet? So I did what any serious academic would do. What do you think? Bravo, Matteo. I started drafting a grant proposal. I got in contact with Claes de Vries, a colleague at our university, who is also one of the best political communication scientists you can find. And we started writing this grant for the Willem Foundation, which is now running. This is a project that's running right now. So I don't have a lot to report yet, but it's already giving us a nice nugget of information. In a workshop with users, we asked them to look at a protocol using a sort of natural language notation, right, to express a communication, or the arrow. And my expectation was that the arrow would lose and they would prefer this notation. And instead, there were a lot of people who wanted the arrow notation. I don't know how else to say it. So, just to, last thing I'm going to mention is that there are still a lot of things to understand about choreographic programming. We are starting a big project. It has just started in June, this big project at the University of Southern Denmark, funded by the European Research Foundation. What are we going to work on? Well, one is reasoning techniques. We want to develop logics to understand and reason about properties of choreographies because, there are a lot of advantages from doing it on that level where the order of interactions is more manifest instead of concurrent code where it's much harder to get. Expressivity, there are still a lot of classes, entire classes of concurrent behaviors that we cannot capture in choreographies, especially when you start having difficult levels of non-determinism like networks losing messages around and exceptions or crashes and stuff like that. So we want to explore that. I've also told you that there's a very interesting question about realizability and projectability, right? Our compilers are simply not smart enough right now. There are a lot of protocols that make sense. They can, in principle, be given a distributed implementation, but the compiler is not smart enough to figure it out. So we want to change that as well, or improve on that. And development, we want to make it easier for people to develop choreographic software in the real world by using our results. Now, these are very connected, these three endeavors. Just to give you an example, without going too much into the details, there are logics out there, especially model logics, to reason and model concurrent behavior, right? So you can use those logics, and since we have a label transition system for choreographies, you can, for example, immediately use a Henderson-Miner logic, just to give an example, to write the specification of a behavior, and then you can ask yourself if this is inhabited in a given choreographic language or not, and you can establish separation results, for example. So lots of synergies. What is interesting for the community, which we are probably going to reach out to you about, is that there's an appalling need for organizing knowledge on choreographic programming, right? Especially the newcomers, they struggle with what are all the papers I should read, and we need to be better at that. So this is something we should probably do together as a community. Everybody is developing new choreographic languages. Everybody is adding a primitive. This is starting to become a process calculi 2.0. We are getting a zoo of choreographic languages. I'm completely fine with that. That's probably necessary. It was necessary for process calculi, and it's still necessary. However, I really started wondering, can't we do sooner than people did it for process calculi? Can't we start developing generalized theories with maybe intermediate choreographic languages such that people can compile to those? It's much easier to compile to a choreographic language from a higher level choreographic language rather than directly to the processes. And this we plan on formalizing in a theorem prover. We call it MEC, mechanized choreographies. And lastly, we need a benchmark. We need to systematize how we compare languages, how we evaluate these languages. There is nowhere to be seen a table, I can dream, a table showing me all the important features that I need to care about for each class of concurrent behaviors that I should care about with representative examples. It's not just us, there are multiple communities who could use this, including the community of session types, the community of process calculi, the community of multi-tier programming. So maybe this goes even beyond choreographic programming. But we really need one, so we should work on that. And that's all I had to say. Thank you very much for listening to me for so long. Yes?
Can I just yell from here? Fantastic talk. Is it done? Okay, fantastic talk. Thank you so much. Really liked it. I'm really an outsider to the community, but it's beautiful. So maybe slightly beyond the reach now, but what's the story of choreographic programming in a Byzantine setting when not everyone is going to obey
We haven't reached that yet. So I'm just going to guess. What the best we have so far is right below. So we have a model still unpublished, but it's been going around for a while now, where everything can fail, basically. Send actions can fail, receive actions can fail, so send and receive omissions. And then we also have omission failures, like where the network can lose a message, right?
Can there be confounded messages?
Can they become what?
Confounded? I think that's the terminology when someone sends the message out of order, but it's in principle like in the protocol, so it's not corrupted, it's just bad.
Yeah, well, we don't, basically what we are assuming is that there are no corrupt messages. There are, if there is a duplicate, it's because you actually wrote the code that generates the duplicate and stuff like that. So that we can handle. But if a process, and we can still guarantee degree of freedom through a type system, which is much simpler than what one might expect because of the overall view the choreographies give you. But if we have somebody behaving maliciously, then we don't know. And I guess, actually, this has been a long-running thought for a while. So first, we had to do the omissions that I'm talking about. And the plan for after that is to go back to 1978, or rather a bit after that, maybe. But we know choreographies or protocols, like in many different settings, that can deal with the Byzantine setting, right? So the idea then is, can we make a choreographic programming language expressive enough to model those protocols, right? And that would be the next step. But it is certainly an open question and a very exciting direction.
Is this on? Can you hear me?
No.
Yep.
Is it online?
Hello.
It's just for the online people.
Oh, it's only for the online people. Okay, good.
Well, we can hear you.
So where does session types fit into this picture? Should we dispense with session types? Just use choreographic programming? Do they complement one another?
Well, there's at least one paper where they complement one, well, multiple papers.
What's your view going
My
forward?
view, my view is that you should definitely keep both. Otherwise, I would never dare to be so arrogant as to, no, but seriously, scientifically now, we're talking scientifically, I would never be so arrogant as to say that I can predict that we can get rid of any of them. We don't know if choreographic programming is ever going to be powerful enough to capture everything, and we don't know if we can ever get rid of lower level languages where session types operate. But I know two things. One is that history tells us we should keep both. We are still running with C code. Session types are going to be fundamental to integrating a lot of unsafe code in the future with maybe choreographic code. Second thing is that you can use session types to type choreographic programs, which we've been doing for a while. And you can use that as interesting interfaces when you project the code, for example, and now you have the library generated from a choreographic program. Well, maybe now you have the library generated from another choreographic program. How do you integrate them? This is still an open question mark. We had some answers using session types. We are probably going to have many more using separation logic and what's not, right? And maybe people you will use extraction to compute the overall choreography of all choreographies in your program. But who is to know which approach is going to work best? I think lots of fun stuff to do in all of these topics, to be honest. So definitely don't stop doing session types because Fabrizio gave a keynote at choreographic programming in Copenhagen. Thank you. Sure.
Yeah, thanks for the talk, Fabrizio. Just one quick question. Are there things that you can't do with choreographic programming?
Sorry. The short general answer is no, because, but I'm cheating, right? We know that there are a lot of interesting choreographic programming languages where you can mix the communication abstraction with low-level actions, right? Like we did in the logic paper. So you can interleave a communication and then put an action towards the environment. If you can do that, you can probably model a lot of things. I don't have a formal proof, but I would definitely try to see if it is possible. Can we model everything just using the communication abstraction? This is a bit like, I guess we'll know when we see it. Just like they do in physics, you know, in theoretical physics. That's the answer they typically give you. What is important there, I think, is the benchmark. But you know, first maybe the concurrency theory community should figure out a process calculus that can express all concurrent behaviors. And we don't have an answer for that either. So it would be nice to have one. Turing completeness we have also for choreographic programming, but it's obviously too coarse as a property. Beautiful question.
Hi, wonderfully presented. Can you hear me all right?
Yeah.
So the work in choreographies reminds me a little bit of work in things like program partitioning, where you automatically take a single program and divide it up into multiple computing components, or even work in high-performance computing, like the languages like X10, where there's an explicit, and now you move to this machine, keep going.
Yeah.
How do you see these various fields as all relating?
Right. I'm not familiar enough with the technicalities of these paradigms. I'm of course familiar with them and that they exist. We did once a comparison with multi-tier programming. There's a difference in how you write code. For example, in multi-tier programming, you don't have this objective viewpoint over the whole system. You jump instead from the scope of one process. You write some local code, and then you can jump to the scope of another process. So the view is always subjective, but you can hop from a process to another. You can, for very simple choreographic and multi-tier languages, you can translate back and forth, right? So the advantage of choreography is that you see the protocol that's going to happen. The advantage of multi-tier is that you can focus on one process at a time, in a sense. When I think about parallel computing especially, I think there are probably very strong connections because we had a lot of interesting results modeling parallel algorithms with choreographies. So then it depends on what you think a process is, because this is a choice you make when you apply choreographic programming. And that's where I would maybe spend some time thinking about. I think that's a very interesting question. So I don't know what the answer is, right? But these processes can be any kind of thing. So if in your hardware you have something that behaves like an independent unit of computation, then you can say that's a process, and then you can write the choreography of how they interact. We could use that even for generating hardware in principle.
Yeah, thanks for the nice talk. I'm a bit curious about the choreographies, because the way you presented this paradigm is still limited to kind of point-to-point communication, and the choreography is emerging basically from those. Now in high-performance computing, where this problem of send-receive has been also discovered some decades ago, the point was to allow specification of larger, let's say, communication patterns. Have you thought about something in that direction as well?
Yes, I just haven't presented them, but you can find, but that's of course a very good point, also because people have written papers about it, so it is certainly relevant. There's work by different groups, including ours, but also others, on multicast, broadcast, scatter and gather. Actually, in one of the papers where we use linear logic, if you think, if you go beyond the duality, the relation that you use in linear logic to check for compatibility of two processes, there's a generalization of it to multi-party compatibility, and there you get primitives like scatter and gather quite naturally. Another follow-up.
Yes, a quick follow-up. You mentioned all the kinds of things that are well known in HPC, in high-performance computing, like scatter, gather, broadcast, and so on. Have you discovered any pattern in this context that is different from those?
No, because normally we go about it the opposite way. We look at what patterns are used in practice, and then we try to model them. I think this is also why we need the benchmark effort, because we need to start writing down all the patterns we have in choreographies to reach out to other communities and maybe check with them, do you have these same patterns? Do you have something more? Do you have something less? Stuff like that, because maybe it will lead to extensions. Maybe these people wouldn't have to reinvent some wheels if we already had the theory for some of that. Something very interesting that came up connected to these kind of things is that there's a work we did on using a type system to model the topology of a high performance computer, for example, such that we could check that a process communicates with another process only if they're actually connected, or they can do a scatter or a gather only if they're actually connected. It's very easy to verify these properties with choreographies, and you get a decidable type system. So I think there is value in modeling these in a language that everybody can understand, at least. And that's definitely another kind of all these communities. This is why I love this workshop. The point, I think, is that we got so much out of two communities interacting in the past, web services and concurrency theory. Now we need to go beyond. Now we are getting to programming languages and distributed systems, but it's still at the very early steps. So definitely something very interesting to look into.
Thank you very much.
Hi, great talk. It was really interesting. This is probably the same answer you gave to the multi-tier question, but just to double check my understanding, would it be similar with sort of the world of these like actor languages where you write an actor system in a programming language that then compiles to a distributed system? Would there sort of be a similar difference between that perspective and the choreography perspective?
So actor languages, as in Akka, for example.
Akka being a framework, but for example, if you compiled like Pony to a distributed system in theory.
Sure. I see actors, for me, live on the same level of processes, in a sense, because you're still writing the behavior from the point of view of an actor when you write the code. And then you have another actor and you write the code from the point of view of that. The primitives are a bit different. They are reactive, typically. So But I think today, actually, there's a talk by Dan on how to compile something that looks like choreographies. Well, they are choreographies. They are just different from what I presented to actors. It gets a bit different when you study the theoretical properties of that, I think, because in actors, people really go out of their way to avoid deadlocks by using reactivity, right? So I think in there, you would want to prove some other properties that you could very likely prove with choreographies. They would be the equivalent of deadlock freedom in process calculi. Only instead of avoiding deadlocks, you avoid, for example, messages never being consumed. These are the properties I would expect by applying choreographies to actor. That was a very difficult question.
The Byzantine behavior. Yeah, well, he got right to the heart of the hard questions, didn't he? Yeah, so my question is kind of related to that, I think. So one thing that that I don't know how to do yet is deal with writing down choreographies for systems where you have participants joining and leaving. And in particular, maybe you have some short-lived participants and some long-lived participants and so on. And I know this is, maybe not something that you can answer briefly, but maybe you could say something about, what hope is there for choreographic programming to be able to encompass that kind of a system? Or do you think that the answer is more like, well, we should just be writing short choreographies for the different subsystems?
I'm very lucky. I can actually answer the question because Marco answered it for me in one of our research talks once. You see these processes we have in Coral, for example. Imagine you could existentially quantify over them. Then you could write a method. Maybe a new process has just arrived. You get the identifier of that process in the result of the method, and it's existentially quantified because you don't know who it is actually. But now you get to code with it, right? And then you can change the dynamic the topology of the network dynamically within the choreography. So that could be an idea. Another idea is that we start writing reactive choreographies, choreographies that get triggered by some external event, and then you still get the process that has just arrived, and it gets dynamically instantiated through some semantics. Now, I said I can easily answer the question. Of course, this is totally underdeveloped, not developed at all. but I think it would be very promising to look into. Now, Sam disagrees. That's the face of Sam disagreeing.
No, I don't disagree.
Thank you.
I don't know. I'm just interested in how you would deal with aliasing in that situation. If you have these dynamically bound participants, how do you know that you're not creating a deadlock by accidentally coupling
in the interest of time? You could either verify it. You will need to look at the local code that triggers the choreography, right? So here, see session types and the software verification. They might come in handy as well. Another thing that I think we should really look into is runtime checks. So if it's very easy to check that you have bad aliasing at runtime. And it's so far, for example, in Coral, the beautiful thing is that it doesn't require any middleware. But we have not investigated at all yet what happens if we start coding a middleware in Coral and using it, right? So implementing this check would be a natural way, and then whoever tries to join and you have bad aliasing, you get a fault, and you get out of there. Even more connected to that, if I can piggyback on your question, another very interesting runtime check is start having runtime agreement protocols where different programs, they check which choreographies they support, and they pick one at runtime, so that we can start having this at the level of transport, even, if you like, if you think about how to apply this on a large scale. So I think in general, this idea of performing runtime checks for compatibility preventing bad properties from, or bad things from happening, etc., really has a future because it sounds very lightweight. Definitely lighter than performing a network communication anyway.
Thank you for the great talk. I think most of the work is based on network communication between nodes. And do you have any application for the low-level stuffs like place and routes and the processing elements, like for the accelerators, etc.?
No. We have, I mean, in Coral, even in the paper, you can find, for example, concurrent algorithms that use multi-threading. Because for us, if these P's and Q's are remote or they are on the local machine,
Never know afterwards. No worries. Yeah, yeah.
Me to W?
I can shout. I can take that one.
Try talking into it.
Ah, no, it's good. Oh, thank you.
So we start with Matteo giving a presentation on a propositional dynamic logic for choreographies.
Oh, yes. Good morning, everyone.
While we have a second, we didn't. We are going to have on the webpage of the workshop some information for the social dinner. Okay.
So, I usually give the last talk of the day every time, and now I'm the first one. It's quite, and I usually get rid of all the technical detail because I'm the last of the day. But now I have to use another excuse, and let's say that too many, and we don't want to see. But there is a preprint online if you want to see all the technical detail. But what I want to give you is an overview of what we have done and why, especially why. And it doesn't work anymore. Oh, okay. No. Okay, so of course it's joint work with Fabrizio Montesi that you may have seen, and Marco Peresotti there. And again, just some motivation of this work, and then I will explain you, give you a simple presentation of propositional dynamic logic if you've never seen before. And then the problem that we found in the application that we want to have for the propositional dynamic logic, so what we cooked as solution to our problem, and some remark and future work. So let's start with motivation. And as Fabrizio told, people were interested in understanding internet data flow, and Fabrizio wrote a project. He won the grant, and I get paid with the grant. And the mission of the grant was empowering citizens in gaining agency about their private data and by building technology which is accessible and actionable. It corresponds, no? So said differently, we just wanted to find a way to distinguish protocols used in internet and explain people what are the real difference. And by distinguish, the project is mostly interested to distinguish with respect to the data which are communicated online because of privacy reasons. So as soon as you want to distinguish program, the first thing that you can think is, okay, we take by simulation, and for example, these are two programs that you can think the dot as the state of the program, and the arrows are the transition, and you can see that these two programs are the same because you can perform the same transition, and whenever you reach a state. But the problem is that we do not want to just talk about the possible execution that you can do, the possible action, but we want also to be able to express that after you perform one action, one instruction of the program, then some knowledge has been changed, especially the knowledge of the agents of the system. And the way to tackle the problem was, okay, let's see what people in security does, because it's the same kind of problem. Instead of trying to understand if a message which is supposed to be secret has been shared, here the message that we are interested in are private data, so let's try to use the same techniques. So there are a lot of work on that. And the main tool user are dynamic logic, because we want this evolution of the program, and some epistemic reasoning, because you want to build up a knowledge of the participant to the network that can be used or exploited by the attacker and see if the protocol has some vulnerability. And generally, you work with expression of this type, which you can read like in a state S reached by the program, there is a sequence of action such that in this case, I'm able to decrypt the message. So you see these are, we'll talk later, but these are, it's called diamond, which are labeled by the action of our program. So we want to represent something like this. So let's take what has been done in the last 50 years now. And let's say propositional dynamic logic as starting framework just to be able to express property about programs. And the idea of propositional dynamic logic is that you mix the propositional reasoning. You see that you have some propositional atoms, conjunction, disjunction, with programs which you represent inside these modalities, which is the box and the diamond. And the program in PDL usually are considered as a regular language generated by some elementary action. And the idea is that programs in PDL are essentially, you can think a program as coinciding with the set of its traces. And again, what is the point of having the program here? And the interpretation is pretty simple, is that you have the usual interpretation as in classical logic. If you have a conjunction, it's true only if both of the conjunction are true, and the disjunction is the same. But here the interesting part is the meaning of programs, and you say that box alpha phi is true as formula if whenever you execute the program alpha, no matter which execution of the program alpha, phi holds. And the interpretation of the diamond, if that exists a possible execution on alpha such that phi holds. So and usually what you do is that instead of doing like in classical logic, in which every formula is even true or false, what you do is you build a Kripke frame, it's called. So it's a model in which you have, the easiest way to think is that you build a model for each state of the program. And in each model, you have an evaluation function tell if a formula is true or false. And then you use the programs as a reachability relation between the words. And for example, you can express property like this one, which I'm saying that this formula is true if either for every time that you can execute beta or gamma, p is true after executing them, or there exists a way, sequence in which you execute alpha and then beta, or alpha and then gamma, such that p is true. So for example, here, this model do not satisfy this formula because you can see that here, of course, you can execute either alpha and then beta or alpha and then gamma, and you have one of the options in which p is true. Here, you are executing beta is true. Here you are executing gamma, beta, and p holds. But here you cannot execute beta or gamma and reach always a word in which p is true. Because here you have an option in which you can execute gamma and then p do not hold. This is the intuitive idea of PDL. And you see that here, in some sense, you have the words, which are the state of the system, and now you can put some propositional reasoning inside the logic itself. Now, what is the problem is that there were no solution suitable to have some kind of PDL working for concurrent programs. And in the literature, there are some partial solution, but the main problem is that there are no solutions which are the parallel, the true concurrency part, the interleaving, and the recursion are handled at the same time. And there was another possible tool at our disposal, which is a paper from who? Montesi and Peresotti. Eva is also here, and Luis, which use OR logic, which is from the 69, but let's say that OR logic you can easily represent as a small part of PDL. And the problem of using OR logic is that you can only express formula of this shape, and you see that there you have a box. And in the example that I've given you from the existence of a possible attack to a security protocol, I had a diamond. This because when you want to check security property, to have one possible failure of the security property is enough to say that the protocol is not secure. So that's why you want diamonds and you do not want boxes. So what's the problem there? Why nobody had a suitable solution? And the problem is, as I mentioned at the beginning, PDL, the programs are just regular languages, and said in algebraic way, clean algebra. And as soon as you put some commutation in clean algebra, and the commutation and the thing that you want to represent this interleaving concurrency, you have an undecidability problem even to decide if two expressions are equal. This was quite confusing for me, because if you come from algebra, finite algebra, and ring and groups, monoids, as soon as you have commutation, everything becomes simpler. But here, because you have recursion and because you have choice, it's a totally mess. So, so in some sense, any possible idea of extending having a concurrent PDL is doomed to fail. And the problem is that here, what PDL does, it's essentially reason about the traces of the program. And so what if we separate the trace reasoning from the operational semantics of the program? So such way, if a program has a problem of the operational semantics, it's not our fault. But we can continue reasoning on traces like we do in PDL, usually. So this was the simple idea behind what we have done. So to take usual axiomatization of PDL and add some axiom which represent the operational semantics of the program. And the idea is that what we do is that we interpret the box alpha of phi as essentially we perform the atomic instruction of the program. So every time I want to execute the program, I just put out one of the possible instruction that I can execute. And now, in some sense, the trace reasoning is on the green part of the program, and not on the red part. So in some sense, I'm encapsulating the problem of the operational semantics in 1 hour place, and I'm pulling one instruction of the time from the program. Such a way, I can use PDL, and I can use the operational semantics. So what we have done then is, OK, there was a recent paper in which they come out with the sequence calculus for PDL. We added additional rules to model this new axiom that we added, and we proved that we have cut elimination, but you may not be interested with technical result. But the fact is that we have a sequence calculus for this logic. That means that you can automatize reasoning by implementing a proof search algorithm to deduce property on the programs. And I was too fast. But we have a lot of time for questions. So the idea is that, as I told you, what we have done is that in this more general framework, we recover PDL as a simple instantiation in which essentially we have an operational semantics on the clean algebra, which is something pretty natural. It interprets the sequentiality as sequentiality and the choice as choice, but in the O plus, not the plus way. And for example, what we can do is that we can simply implement this operational PDL with the CCS. And what you have is just you take the semantics of CCS and you plug inside this logic. And the only thing to do is that almost nothing is that you have to consider the silent action plus the natural element of the clean algebra with respect to the sequential composition, of course. And interesting, there were some work in the literature in this direction, but there were some problems that they were not able to use the parallel composition as supposed. The work in the literature only used the parallel at the top level. And most of them just rely on the fact that you can interpret a P parallel with Q as P followed by Q or plus Q followed by P. And the problem is that when you do that, of course, you have an exponential blow up of any representation of the program and any test of program. And most of them, they do not they really use recursion, but more iteration. And the reason is because in clean algebra, you have an operator which is an iteration, is not recursion. So the idea of the previous work was, OK, we take PDL, and in the clean algebra, we add the parallel operator. And as I told you, there are problems there. And then, since this is a workshop on choreographic programming, we can now plug choreographic reasoning inside propositional dynamic logic. And I think you all know how choreography works. And now we have at least the basic level of what were the initial motivation of the work. So now we have essentially we have this new toy. What we can do is that once we formalize the result in this new logic, because if we want application, we have to be sure that everything works, we can add the epistemic reasoning. So now what we can do is that in the propositional dynamic logic, we can start to add proposition, which talks about the knowledge of the participant in the protocol. And what you can do, what you can expect is that if I give you a choreography, I'm able, in some sense, to predict all the knowledge in the limit of the reasonable, to have a way to extract the possible knowledge of the participant after I will execute the choreography. And then we can start to use result on differential privacy to say, OK, if this is the common knowledge in the network, what can be inferred by this knowledge locally? And have back to the solution of the initial problem, and maybe have, instead of just telling the user what are the endpoint of the message exchanged by cookies, we may be also able to give some insight of some derivative knowledge which can come from the fact that you granted some information to one website and to another website, but they may communicate, and maybe by knowing just a part of information, they're able to know something else. And thank you for your attention. And if you have any question, we have 3 minutes.
Working? OK. We are open to questions. If there are none, I can. Do you have one? Yeah.
Hello? OK. Hi, Matteo.
Hi.
So I just want to make sure that I understand kind of the application of this work to choreographies. So if I understood correctly, you're saying given a choreographic program and given a predicate that's like P knows this, Q knows this, R knows this at the same time, you're asking, can we find if there's an execution that will reach that state where we all have the same knowledge at the same time?
So what you can write now is that, for example, for any execution of the choreography using the box with the choreography inside, let's say true, then P knows something, Q knows something else, and R knows something different. And now you can formalize this inside the same logic, and you have an inference system which should be able, if the problem is undecidable, so you cannot go any further, but if this configuration is reachable, should be able to show you a proof that this configuration is reachable.
So specifically, if they can know those things at the same time, right? Because otherwise you can just execute the choreography and see if after a certain amount of time they have that.
Yeah, there is also another problem that knowledge may not be monotone because, for example, what you do, you communicate that, for example, a variable on a value on a variable, but then the choreography will update the variable. So that's kind of non-monotonic reasoning is still beyond what we have done. But again, to have all this reasoning, all this epistemic knowledge, we should have at least a way to be able to express. And what we have done, we create the way to express this kind of properties.
Do you have a clear idea how differential privacy would be used in such a system?
So my idea is that once that you have a way to say from the execution of this choreography that exists, or any execution of this choreography will lead on a situation in which the participant has this kind of knowledge, now you can use this, let's say, base of knowledge of the participant to then build up an expert system on that. So for example, if you know that P now knows your address and your name, and now it knows your complete address, this is quite easily. But for example, you can use result on differential privacy that they know that you're IP, they know that you visit that website, and there were results, for example, based on your web history, they were able to deduce your address, something like this.
Oh, so this would be extending what is knowable.
Yes, yes, yes. So it's
okay.
This is the first layer. Now, on top of this layer, we can now use this base of knowledge to build up to the reasoning using differential privacy results. But the problem was, okay, how can I be sure that after executing, I have this configuration of knowledge in the system? So what PDL is needed here is to be able to be sure that you can have this configuration of knowledge on which you can reason.
Cool.
Maybe this is a not so smart question. Why is decidable equality important? There was a reason for having the operational dynamic logic.
It's the same problem of halting problem. You want to know when the program ends. So here you want to know, it's a pretty simple question. I'm telling, is it true that every time that I execute A and B, I can have the same results? So it's a way to say that A and B are equal. And in this setting is undecidable. And I think it's also undecidable in bisimulation in general. So it's just to say we are not solving all the problems of the world here. You still have the problems that are outside.
Thank you.
Okay, thank you very much for the presentation and your questions. We move to choreographic programming in model type theory by Maxime.
Do you need it?
Yes, please.
Do you need it?
Sorry.
They give to me, I was going to give it back. Ah, yes, also this one.
You can shut it off. Yes, very good. Okay. Does it work? Hello? Slightly closer. Okay. Okay, hello, now? Great. So, hi everyone. I'm Maxim, and I like dependently typed programming languages. So that's why I've been thinking about dependently typed choreographies and how one would go about making such a thing. And well, I found a way and I started building it. It's going to be Kami. It's very early. But I want to tell you about how, well, yeah, how I did it. And the thing which allowed me to do it, because dependent types are very complicated, and I found MTT, which is modal type theory by Daniel Grazza from last year, which is his PhD thesis, and it's It's a type theory with dependent types and which allows for arbitrary modalities. And I found a way to use his general framework to find an instantiation of it to reproduce choreographic programming. And this way you get the dependent types for free, kind of. Well, and the journey started with the functional choreographic programming paper, which Fabrizio already introduced, which is the core lambda programming language, which is a functional choreographic programming language. And this gave me the idea to think further to the dependent types. And, well, how do we do this? There are kind of, like when you think about it, there are two worlds, two modes in choreographic programming. We have the code, which is running locally. It's like we have natural numbers, we have sum types, we have function types, products, whatever. And we have the global world, which is the different locations and nodes and processes. It's like we may have natural numbers located at some node U. We may have some globally distributed knowledge of choice. And of course, we have function types, which are our choreographies. And I take this distinction of two worlds very seriously. So the types of Kami are defined as follows. We have two versions of types. Oh, well, yeah, let me tell you. I write triangle for the local mode and circle for the global mode. The triangle is like a piece of cake, and the circle is like the whole cake. So we have our local types, which are whatever types we want to have, like functions, products, and so on. We, like in the full MTT, there are also dependent types there, but I skipped them for the talk. And we have the global types, again, all types. And now, so the point is, all the standard types have perfectly standard terms and typing judgments. They're exactly the same. They're only the magic comes in these two new type constructors. One is the at type constructor you might have seen from choreographic programming, where we have a local type at some location. And I also introduce a new type constructor, which takes a global type and puts it locally. So the meaning is we can have, when we have a choreography, we can represent it locally. Like the projection to each location, we take them simply as a tuple and have it locally at the location. So yeah, exactly. So the meaning of the at constructor is, of course, like when we simply project it into a set. If we have a location U and project it to location V, of course, it's the interpretation of A if they are same and the unit type otherwise. And on the rest of the type constructors recursively. And now the interpretation of my new box constructor is a tuple of all the local projections of the global choreography type X, and recursively on all the rest. Now, how can we work with these modalities? So first, the idea is when we want to construct something under an at U modality or under the new box modality, then we can only use variables in the context which are under the same modality. This means that, for example, we want to construct a tuple, like a global tuple where A is under U and B is under U. Of course, we can use such a tuple at the U location. And we can also have the same, like the reverse function. And just as well, if we have a local function located at U, we can turn it into a choreography mapping A at U to B at U. And the same thing works with my new box modality. Now, this is the default behavior of modalities in MTT. And without adding further things, we of course cannot build a function which creates A at V from a value A at U, right? Because we cannot, like, this should involve communication, and we haven't added communication yet. And also, like, box of A at U is a local value. It's like the choreography where the choreographic type, let's say, where A is at U as a locally defined choreography, and this is simply the type A. Like, also removing modalities randomly is also not allowed in, like, without adding further primitives. Okay, so this is how the basic modalities work in MTT. Now we want to add actually the communication primitives, right? So for that, I want to introduce some notation. I told you, like, the add modality takes local types and turns them into global types. Now I want to allow to compose modalities. So we can take box at U, goes from global to global. We can take even 3, like at U, box, at V, local to global. And I also allow the, like, identity modalities which don't change the type. So now if I have an arbitrary modality which goes from one mode to another, and I have a type at this mode M, then I write these angle brackets for applying this modality to this type, right? So for example, if I have natural numbers and apply this triple modality, then I'll get n at U boxed at V. Okay, so now let me introduce the communication, well, the 2 primitives with which we can actually write choreographies where things interact. And the first one is actually one without any communication. It just, like, I introduce this new primitive where I say if I have a local value of type A, then I can put it into a locally choreography where this type is at any location. I might, like, it's like scheduling. I might schedule it to U, to V, to W, wherever, but it's not there yet. It's just, like, in the type tracked where I want it to be. And then here's the main thing. I have broadcast. If I have a global choreography type X, and I have it boxed at a location U, then I can turn it, like, into the actual choreography type X. And so this primitive involves sending the projections to each participant involved in that choreography. Yes, and now I have to tell you that actually I don't add only these primitives, but I allow them to be under any modality mu, right? So before we had A to this thing. So now actually I say that, okay, under mu, and here again under mu. And this whole thing under nu, and here again under nu, because I need to be more flexible and do things under modalities. Right, that's it. That's kind of how I recreated choreographies in MTT. So now let's see an example. We can reproduce the communication primitive from core lambda by, like, the type is, of course, we want to send something from U to V. And how we do it? Well, given such an A at U, we first prepare, like, schedule the A to be located at V. So we have this triple type. And then we simply broadcast, like, we actually broadcast this choreography to, well, in this case, only V. And we have our function. Now, of course, this thing is, it's not only communication, right? It's a little bit more powerful. And in fact, this can reproduce the problem of core lambda was that we need to somehow take into account knowledge of choice, right? When one process decides to do something, other involved processes need to know about, like, what choice it was. And we can reproduce that without any partial projection functions, but it's just already available built in the sense that we have both a local sum type and a global sum type. Like, if I project this, if I project this sum type to all components, this means, okay, well, the node U has knowledge of A or B, and all other nodes know nothing. But when I project this sum type, this means, well, the sum is global, means all have knowledge of, like every process have knowledge of the choice. But the actual data is, of course, only located at the node U. So the point of like communicating choice is just a matter of turning such a sum type, like into such a sum type, which means I tell the other processes which choice I want to make. But I don't necessarily communicate the information which I only locally want to continue with. So, like to write a function, is very easy, but I skip because it's a little bit long in the pure MTT syntax. So the point is that we first construct a function which takes our local type into a boxed at U thing, and then we simply do a broadcast after that. And yes, I call this whole thing globalize. Well, so the thing is, we can do the same thing with other data types. If we have a list which is only locally known at U, we can, in the same way, globalize it to have a global list where all participants know, know the length of the list in a sense, but don't have the data. And again, when I do a global pattern matching on this list, all participants know which branch we take, but only my U has the actual data. So in this way, there was an example in Core Lambda where there is a function, an f, only available remotely at node V. And we have some data at U, and we want to use this function at V to map it on this list. So in MTT with my instantiation, this would look like, first, we can globalize the list to be able to globally choreographically pattern match on it. And then we can simply do, well, recurse that's kind of the logical thing, right? When we have we can recurse on the list, communicate each element individually to V, and use f there, and call our map recursively, right? Okay. So now this has been one instance of modal type theory, and the thing is that generally modal type theory is parametrized. We have the definition starts with, well, let's see what a mode theory is. And for every mode theory, you get one instance of MTT. And the mode theory is, well, it's first a set of modes. In our case, it's only local and global, right? Then we say, for every pair of modes, we decide on the set of modalities between them. In our case, these are the add and the box modality. And then we say, well, between modalities, we allow transformations. In my case, these have been the prepare and broadcast transformations, right? So now with this thing, it's very easy to extend what I have told you, to extend with new features. For example, well, yeah, this is how my MTT looks. Right, the modes are the local and global. Here are my modalities, and prepare and broadcast are my transformations. Now, for example, let's add a new feature, which is common knowledge, common locations. For example, we might have a data type located at two nodes, and both nodes know its value. So very easy in MTT, what we do is we say, well, our add modality now takes subsets. And we add a new transformation, which says that if we have a subset V of U, then we can narrow the globally known A to one subset of the participants. Very easy. You just put in the new mode theory, you get a new full type theory, right? Or, for example, until now, my global world always involved all processes. even those nodes which don't participate in the choreography, like will have to communicate, will have to receive the knowledge of choice, right? We can do a little better, and we can say, well, actually, we have global modes for every subset of locations, and then we say, okay, we can include, of course, a choreography like involving U, where U is a subset of V, is also a choreography involving V, right? And then we have a more fine control over which nodes like actually communicate, and we can control this behavior. So in conclusion, choreographies fit kind of extremely well into this framework of MTT, and it's very easily extensible, and we get dependent types for free. The downsides are that the endpoint projection is a little bit more complicated because the types allow for more freedom. And this is kind of what I'm working on, still work in progress. So yeah, that's it from me.
Thank you for your presentation. We are open to questions.
Hi, thank you. This was a really interesting talk. I'm a little bit curious about how I should interpret something like A at U boxed at V.
Yes.
Can you give me a bit of intuition about how to interpret that?
Yes, sure. So where did we have it? Here, right? It's so first the outer modality says that this whole thing is located at U, only at U. Now the box says that now we want to have a choreography, right? We want to have a whole choreography, but this whole choreography is actually only a single value A, which should be located at V. It's like into the box, you could put a function type, right? You could put a function type which maps things from many locations to each other, whatever, right? But the only thing we put inside is this value A located at V. It's like at U, schedule the choreography where A is at V. Oh, wait. Sorry.
Thank you for the really nice talk.
Yes.
Could you go to the slide where you had globalized list?
Yes. I guess that's...
So this, yeah, this got me curious. Also, your previous slides about how to represent knowledge of choice, because in Core Lambda we have these distributed choice types. I mean, I'm quite sure you could write a globalized list in Core Lambda, right?
I think you don't have because you only allow for the adds at specific locations.
Yeah, but you can write a pair where the different components are at different locations, and then you can write a list of tuples with different types at different locations. And we use this in the follow-up ECO paper to show that you can model distributed knowledge about the choice. You just mention it, right? So I was just wondering if you had any thoughts about what are the real expressivity differences between programming like this and programming by using fine-grained knowledge choice, where you communicate this knowledge through selections and stuff like that. Did you look into it, perhaps?
The thing is, the fine-grained control, like from my point of view, it's I don't see where it's necessary, because usually when you want to program like from a normal functional programming point of view, you already have in your mind the different sum types you want to pattern match on, and the goal is only to get the information to those nodes which need it. So from this point of view, the fine-grained control is kind of not necessary in the sense of you can reproduce all those select statements again with this thing, right?
Thank you very much again for your talk. And now we have Eva presenting Choreographies Meet Communication Failures.
Eva, and yeah, as you can see, I am presenting choreographies meet communication failures, which is joint work with Fabrizio Montesi and Marco Casotti, who are sitting here as well. So if there are any problems with it, it's our fault. Yeah, so you've probably seen something like this if you've looked at anything about choreographies. So the communication works in choreographies is you write something like this, which says P sends 3 to Q, and Q stores it in X. And then you project this to two different primitives at P and Q. So at P it says send 3 to Q, and at Q it says receive from P and store in X. And then, at the local level, we assume that these two synchronize, and Q then just has 3 stored in X. As it turns out, sometimes that doesn't happen in the real world. Sometimes communications fail. And then we ask ourselves, well, what do choreographies look like if, they have realistic communication? What does that mean in our case? Well, it means A, it's synchronous, and B, it can fail. And we consider 3 different kinds of failure. Number 1, send omission. P tries to send, doesn't go well, the message never reaches the network. P knows that this has failed. Second failure, receive omission. Q tries to receive, doesn't have anything to receive. The message hasn't reached Q yet. Q knows that this has failed. And the third is omission failure. P thinks it's sent something successfully, but somewhere on the way to Q, the message gets lost. And neither P or Q knows that this has happened. So now we ask ourselves, if we don't have this, nice little one singular communication primitive, what's even the point of using choreographies? What guarantees can we get? Are there any of these guarantees that are easier to get for choreographies than for just writing code separately for our participants? So what I'm going to tell you about our contributions here. 1, we have a choreography language which has failures in the semantics. 2, we have some choreographies written in this language which describe ways of recovering from failure. And 3, we have a way of statically analyzing these choreographies, which, hopefully we can get some guarantees that are interesting, and we can take advantage of the fact that we have written our program as a choreography. So first of all, what does our language look like? Looks something like this. So we traditionally, you have our communication here. So in our language, instead, we have 3 steps to a communication. First is we declare a communication. This communication is going to be called K at P and K prime at Q, and it communicates an int. We have a type system. I'm not going to talk about it. It's not very interesting, but it's there. It does what you'd expect it to, more or less. So once we've declared a communication, we implement it. First by writing that P sends 3 on K, and then Q receives something on K prime and tries to store it in X. So I'm going to go through the semantics of this in a minute. First, gonna just talk about what K and K prime are, because these are the interesting parts of our syntax. So K and K prime identify the communication at P and Q respectively. So what we do is that P and Q count their communication. So this is K is the first, P knows that K is the first communication with Q, Q knows that K prime is its first communication with P. So when P sends something on K, it tags this with a 1, because K is the first communication, and correspondingly Q, then when it's trying to receive prime, it only looks at messages that are tagged with 1 and are from P. So that is how, our communications, we avoid any mix-ups where P and Q disagree on which communication is which. And look at that, we already have a benefit to using choreographies, because since we only count when we have this primitive declaring a communication, and since this is one local action each at P and Q, and this is the only way P and Q can increase their counters for their communications. We can ensure that the counters stay in lockstep. Mm-hmm. Oh, sorry. Whatever. Sorry, yep. Anyway, so let's look at our semantics. Our semantics looks like this. We have triples consisting of a choreography C, a local memories of the various processes, sigma, and a set of messages in transit K. And the messages in transit looks like this. So P is sending to Q the mth communication between P and Q, and it's sending 3. And this message is, if it's in K, it's in the network, and it can get lost, or it can reach Q. So what does our, one, there we go. So this is our desired outcome of our little communication. So what we're hoping is that starting from up here, we have our, our little choreography that declares a communication and executes it. And what we want to happen is that first we declare, which updates sigma prime, so the counters for which were 1 before are now both 2, and also we have the state of frame 1 from at P communicated with Q is bottom, which is to say we have not sent anything, and conversely at Q we have a receive frame which also has not received anything and therefore has the state bottom. From here, what we would like to happen is that we send something which updates the send state to yes, we have executed a send, and adds the message to K. And then we can move the message, communicate it, so that it gets to the receive state of Q. It is ready to be received, and Q can execute the receive and say now X is 3, and we have successfully received 3 according to the state of our receive. Obviously, since we have failures, this is not always what happens. So one thing that might happen is that we fail to send, and instead we don't add the message here, but we do still take the send, and we also don't update our state so that the sender knows that it has not yet succeeded in sending, and there's no message. Another thing that can happen is we might try to receive and too early. So if since Q is not, Q and P can execute concurrently, so Q might try to receive already before the send has even happened. And in that case, again, nothing really happens. We just consume the send action, and we're stuck here. And then we can send unsuccessfully, or we can send successfully and communicate. But since our send has been consumed, we can never properly receive it. Third, failure, communication. We might have an emission failure, so that just means our message here, instead of going to Q, gets lost. And goes away. Okay, so at this point, what P and Q might want to do is they want to know which of all of these possible end states we're in, because their future behavior will depend on this. For example, they will try again to send, or try again to receive, or or they'll continue, hopefully, if they have everything has worked out. So how do we do that? We have some conditionals. So our conditionals are, first of all, we have a conditional on the sender. If we've successfully sent, then we do this, otherwise we do that. If we've successfully received, then we do this, otherwise we do that. If we've successfully received a specific label, so that's how we communicate a choice at P to Q, we send a label, then we do this, otherwise we do that. Of course, we can't check locally whether messages have been lost, so that makes things more complicated, but we can at least check for some failures. And using these conditionals, we can program some recovery strategies. One benefit from having separate send and receive primitives is that we don't have to try the same number of times to send as we do try to receive, which is useful because if the send fails 5 times, well, the receive might still succeed the first time. So no point in receiving too many times. But we still want to be able to program something that kind of looks like this little arrow here, syntactic sugar. So one way we do that, we have, for example, a send with exponential backoff. So that looks like this. We define this as a recursive function, send with exponential backoff. It is parametric on the process and the frame we're using. And it is tagged with the expression because making it parametric on the expressions is a pain in the ass, and also it doesn't really relate to what we're doing, so we haven't done that. So what we have is, if we have not yet succeeded in sending, then we wait from 2 to the power of n time and return a new n, which is n, the previous n plus 1. And then we try to send, and then we call recursively. Once we've succeeded in our little in sending, then we finish. Another thing for receive, we might want to receive with a timeout. We try to receive the timeout. Again, Q tries to receive on K prime. So if we've not yet timed out, which is to say timeout is more than 0, and we've not yet succeeded, then we update our time, try to receive, and use the stored time to remove some time from the timeout and call recursively. And we can use these to get this little arrow here. So what this says is that P is going to try to send to T and going to try to send to Q something of type T that has, and Q is going to have a timeout of T. So we declare the communication. We set n to 0. So that's our time that we have to wait to send. That starts out at 0. We send our timeout time to T, and then we call our 2 functions. And you can write, we get something resembling the standard communication primitive for choreographies. So now, what do we want to hold for our choreographies? Normally with choreographies, what we want is A, an operational correspondence between our choreography semantics and our local semantics, and B, deadlock freedom. Now deadlock freedom, very easy. You can just fail, never deadlock. Everything's very simple, so that's not very interesting to try to prove. Operational correspondence between choreographies and local semantics, also not that interesting, honestly. We have, the main thing we have is this gets projected to one action each at K at P and Q, and they count the timers up, they create the frames, they initialize same as they do in the choreography. Pretty simple, so not that interesting. What do we want instead? Well, what we would like to have is that our communication is at most once and best effort. So we don't want to be trying to receive when there is no chance that the message has been sent yet, and we also don't want to be trying to receive something that we have already received, basically. And also, we don't want any unnecessary conditionals, because we don't, well, you don't want to be writing extra code, do you? So how do we get that? We need some static analysis. We have what we call our robustness system. And robustness looks like this. I'm sorry, it does. You can't get out of this. It is technical. There's a lot of things in there. But yeah, this is what we need. So what we have here is something that sort of looks like a Hoare logic, in that we have F0 being the state or before we execute C, and F1 being the state after we execute C. So what is in these states? Well, so these kinds of pairs of a frame, K at P, and the current possible states of the frame. So when we first initialize it, it puts on a hat. And it doesn't take the hat off until it is certain that it is done with whatever communication it has to execute. Additionally, what we have here is a label L, which means that it is possible at this point that P has sent L on K, but we don't know because the hat's still there, so we're not certain. It could be that nothing's happened. On the other hand, if you don't have a hat and you instead have just one state, which is a bullet, that means we are certain that a value has been received. So how do we use that to get our, need P and R first. P is a list of connected pairs of frames, so a sender and a receiver. You need to know which frames are connected to which, and R is the judgment of our predefined processes. So, for example, send with exponential backoff, you start out not having sent anything on the frame, and by the end, you have sent something. So how do we ensure there are no unnecessary checks? Well, when we're checking whether a receive has succeeded, we need the state before that to be that it can it has the hat, so it can potentially not have done anything, but it also has something that isn't the hat, so it can potentially have done something. And then we split these two states for the two continuations, because which continuation we use depends on which state we're in. How do we check that we only receive at most once? Well, also pretty simple. So when we're receiving something on C, what we do is we check that it must have a state which is only the hat, which means we are guaranteed that it has not done anything. And then we add whatever its corresponding sender has in its state to the state. And then we need to use the conditional on the previous slides to remove this and go into C2 before we can send again, because we need, otherwise, because the requirement of the state down here. How do we check? Well, there are some systems where you don't have omission failure. In this case, you might want to send at most once. So for that to happen, we use our send rules, and we again ensure that the state is the hat, and then we add a new whatever S is to the state. Very similarly, best effort communication is also ensured by our receive rule, because it checks that that there must be something in the in queue in the corresponding receiver. It must have at least tried to send something. It must be possible in this that it is in a state where it has sent something. That's what best communication is. So, conclusion. What is the benefit of using choreographies in this setting? Well, we keep our frame counters synchronized. We can write our custom communication errors and syntactic sugar, and we can do our static analysis, which we could not do if we had two separate programs, or multiple separate programs. Sorry, just finishing. Give me 1 second. And what guarantees do we get? Well, we get the guarantee that we do not have any dead branches. We have at most once communication, and we have best effort communication. All right.
Thank you for your presentation. We have time for one question, if you have it. Thank you, Andrew.
Can I? Okay. So thanks, Eva, for the nice presentation. Just one quick question about the language. You have these send and receives that are kind of decoupled now, which goes a bit against the idea of choreography.
Right.
Maybe because I'm still a bit confused, of course, but where is the choreography there? I mean, these send and receives, can they be scattered anywhere in the choreography, or they have to be close to this case? Was it frames? Do you call
frames? Them? No, I mean, you can create a frame and then use it much later in the choreography if you want. So the main thing is our this receive rule. What we ensure is that before we try to receive, there must be one send already have happened on the same frame. So that's the main coupling between them. And then obviously that we have this declaration which happens separately at the two, but it happens sort of the same number of times. So you can always make sure that they agree on which communication is which, basically.
Okay, thanks again for your presentation, Eva. Next, we have Andrew. Talking about CORPS, a core calculus of hierarchical choreographic programming.
All right. Hello. Thank you, everyone. I'm really glad to see so many people here. It's really awesome to see everybody and have this workshop. So thank you to the organizers for putting this together. I'm talking today, I'm Andrew Hirsch from the University of Buffalo, where I'm an assistant professor. And I'm talking today about CORE, a core model of choreographic programming, of hierarchical choreographic programming. And I'm going to explain what hierarchical choreographic programming is during this talk. But really, this is a talk about propositions as types. And propositions as types is one of the most powerful ideas in theoretical computer science. Not only is it an immensely powerful idea in theory, it also runs some of our most important pieces of impact, like theorem provers, Coq, Lean, Agda. And what propositions as types is, for anybody who might not know, is essentially a connection between logic and programming. It says logic and programming are exactly the same thing. There is no difference. Propositions, the formulae you prove in logic, are types that you give to programs. Proofs are those programs. And I say that, with all due respect to Fabrizio and his previous work, choreographic programming needs propositions as types. We've made really big strides in the last few years in terms of functional choreographic programming, which adds choreographic primitives to lambda calculus. And this suggests that a lot should be possible with regards to propositions as types. And moreover, I really think that propositions as types would help the choreographic community. First of all, it would really help guide the design of our languages. Think about in the session types world, how much the connections to linear logic have really helped guide how people should create new languages, new types. It would also help us be able to prove things about our choreographic programs. If we had a nice propositions as types principle between choreographic programs and some logic, we would actually be able to do a lot more proofs of our programs. And frankly, it would help us sell choreographic programming. Who doesn't get excited by propositions as types? It's really cool. So what's missing? And in order to understand what's missing for propositions as types connection here, I'm going to compare Pirouette to lambda calculus. So Pirouette is, I would say, the first functional choreographic programming language. It beats out core lambda, which was concurrent work, by a couple months. So not first by much. If we look at Pirouette compared to lambda calculus, there's one addition, just one. And that's the located type. We've heard a lot about located types today. But a located type just takes a process name and a local type, right? A type of some local program that has no send and receive communications. And it packages them up into a choreographic type, something that's global to the entire system. What do we do with these local types? Well, we can introduce them by having located expressions run this local program at this location. We can eliminate them using pattern matching let or something similar, allowing us to bind local variables and reuse them later in further local computations. And we can send and receive. The standard choreographic send and receive primitive here. In both of these, C1 has a located type. So this is something that's going to compute to some value on some location that can then be sent on or bound to this local variable. And so the thing that we really need in order to get this propositions as types connection is a logical version of a located type. And, well, we actually heard about the solution earlier today. It's modal types. And modal types are really brilliant for this sort of thing. And frankly, if you look at choreographic programming, functional choreographic programming especially, and you know modal logic, this is pretty clear, but there's a problem. What modalities do you use? There's a lot of modalities in the world. Modal programming is super, super powerful. For instance, you could have epistemic logics, conditional logics, deontic logics. What do you use? And what I'm using in this work, and the thesis of this work, is that located types act like what are called doxastic modalities. And doxastic is just the fancy philosopher word for belief. So these are modalities of belief. And we're going to write A believes phi instead of box A phi because I prefer believes. And in fact, I'm going to be even better. I'm going to draw pictures. I'm going to have Alice here believing phi to represent A believes phi. So if you see a lot of that, that's what it means. And there's a core thing that can happen in doxastic logics, which are nested beliefs. So if you have Bob here, he can have beliefs about Alice. For instance, here, Bob believes that Alice believes phi, or believes not phi, excuse me. And in fact, Bob can't just, it's not just the case that Bob can have beliefs about Alice, but Bob can be wrong about his beliefs. So for instance, Alice actually believes phi, and that's okay. And this is really fundamental to doxastic logic. First of all, nested modalities are just super important to all modal logics. And the fact that these beliefs can be wrong is really what allows us to have doxastic rather than epistemic logic, right? An epistemic logic is a logic of knowledge. If Bob was always right about his beliefs, we would be arguing about things that he knows, not just things that he happens to believe. But this is a big mismatch with Pirouette. After all, in Pirouette, the local types are local. They come from a completely different language. So you can't start nesting things inside of this. So Pirouette just can't express nested beliefs. And well, if you know the literature on functional choreographic programming, you might ask, well, can core lambda just come to the rescue? After all, in core lambda, we have the same language used for local programs and for global programs. But those local programs are restricted so that they are truly local. So they don't actually solve this problem. You can imagine using polycore lambda, which is a polymorphic variant of core lambda that Fabrizio and Eva and I worked on. And this gets a lot further. You actually get something that looks a lot more like an earlier talk that we saw if you tried to take this route, I think. Although I haven't tried it, so I'm excited to hear more. But we can solve this problem by instead recognizing a phenomenon in doxastic logics, which is that nested beliefs create new agents. And think about it like this. Alice here and Bob's version of Alice have different beliefs. So they must be different agents. So somehow we have Alice and a version of Alice that lives inside Bob's head. You can think of Bob as simulating Alice. So what we need somehow is a hierarchy of agents that we can reason about and program with. Hence, hierarchical choreographic programming. And what you get is a hierarchical topology where Bob can have sub-agents, Alice. He can also have a sub-agent named Bob, that's okay. Alice can have her own sub-agents, Alice and Bob. And in fact, these can live all inside some world of ground truth. Right? You can just talk about things that are true. Nobody believes them, they're just true. And that might include the fact that Bob believes some things. And this might seem like a lot of artsy-fartsy, airy-fairy, I'm doing philosophy now, where's the computer science? But real networks have these tree-like topologies that I'm building, right? So you might have network terms that reference an entire network, but you might also have servers, and those servers might have cores, and you might want to program each of those cores independently, but you need to know which server they're on. So realistic networks have this sort of tree-like topology. So now we get to the big question, how do we represent hierarchies? After all, we now have A.C has type A.tau, where C is a choreography, and tau is a choreographic type. And we have to somehow say, well, this is only true if C itself has type tau in some context, but what context? After all, A should only have access to their own part of the context. They shouldn't have access to what's going on Bob. So what do you do? Well, you can do some complicated proof surgery here, mess with your context and work something out. And in fact, this is exactly what Pirouette does. And it works at Pirouette. But it turns out once you start having these hierarchies, it turns out to be very non-compositional. So what do? It turns out there's been work on this recently. And it draws on something old from logic called Fitch-style proofs. They come from this book. And Fitch-style proofs in this setting come with a notion of modalities, which is basically a path in this hierarchy of agents. So it names some particular agent in this hierarchy. And this actually comes from some previous work I did, not at all involving choreographies, but on something called authorization logic. I wrote a logic called FLUFFLE, the flow-limited authorization first-order logic. And it's a type of doxastic logic. We call these generalized principles in there. You then modify the context. We're used to contexts mapping variables to types. And they're still going to do that. But everywhere that you map a variable to a type, you're going to write down who owns it. Where is this located? And we're going to add a new type constructor, this lock_im, that represents a restriction to im's view. Now, this might seem pretty complicated, but it has been shown in a paper that was referenced earlier today to scale all the way to dependent type theory. So we know that it's actually a very compositional way of doing things. So we can use this to fix our first mismatch, but we actually have another mismatch, which is, well, we want choreographies. So we want to be able to send data. And what sending data does is just change the modality. But doxastic logics, most of them, have no native way of changing modalities. And this is where the authorization logic comes in. So authorization logic adds one thing on top of doxastic logics, which is adds trusts. Bob trusts Alice, which they write as Alice speaks for Bob. And what this says is that whenever you know that Alice believes phi, you can use the fact that Alice speaks for Bob to derive that Bob says phi. In other words, we've just communicated along a channel. So doxastic logic, authorization logic is doxastic logic with trust and communication. And trust acts like a channel. And in fact, choreographies correspond specifically to authorization logics. So I'm currently working on a language called Core. It's named after Corps de Ballet, which is the lowest rank in American ballet. I wanted something involving ranks and dancing. I also really like the fact that I could call it Core, a core model of choreographic programming. And this is designed to reflect these hierarchical topologies while having a propositions as types relation with authorization logic. Now, what we have so far, what I've described so far, is a connection between the types of a language like Core and proofs in doxastic logic. And you might ask, is this enough? And the answer is no, for a reason that Fabrizio hinted at earlier. We've not talked about the mechanics of the logic at all. So we need some way of saying, hey, if you beta reduce over there, something happens over here. And what is that thing? Well, it comes from an idea from logic called natural deduction and sequent calculus. Proof systems can be natural deduction or sequent calculus. They're equivalent in strength. And natural deduction is what you get when you just take the typing rules of lambda calculus and view it as a logic. But sequent calculus has something special, because it has this cut operation. And cut is basically just substitution. You can just say, hey, I'm allowed to substitute variables in, which everybody would like to be able to have. But sequent calculus doesn't just have cut as a rule, it actually admits cut as a rule. What does that mean? It means we have no expressive power by adding cut as a rule. In other words, we can take proofs with cuts in them and remove the cuts, finding cut-free programs. And cut-free sequent calculus proofs are normal form natural deduction proofs are normal form programs. So in other words, where normal form programs mean there's no beta radices available anymore. So in other words, beta reduction is cut elimination. And this works well for lambda calculus and logic, where we say, look, if you beta reduce, we're going to consider these to be equivalent programs. We don't accept any difference between them, really. But with communication, this is a little bit more awkward, right? If I have A sends 3 to B, I can reduce that to just B has a 3. But like, are we really willing to say that those two things are equal? This seems really awkward, right? After all, the communications are different in these two programs. And it doesn't seem to correspond to cut elimination in most authorization logics either. It seems to correspond to something a little bit different. So there's a couple ideas I have here. I told you this is a work in progress, so I'm going to tell you ideas I have, and I don't know which one's going to work out. The first idea is to separate communication, reduction, and beta reduction. Have them as separate things, and require normal form of communications before you start normalizing with beta reduction. And this works out really well in logic. It's what both Danny Gratzer and I do in our respective works in 2020, completely independently. We discovered this. The problem is that communications and beta reduction rely on each other. So this is fine for proof surgery, but for normalization, it's kind of awkward. We could use some notion of tracing and say, well, in order to consider them beta equal, they have to reduce with the same trace. Concurrency theory uses these sorts of ideas all the time. It really complicates some ideas in type theory, because now you want to talk about programs being equal, not just when they reduce. Another idea, communication is just pure. Yeah, those two programs are just equal. Bite the bullet. In fact, in choreographic programming, in some sense, it is just pure. It's just an operation on a particular type. You just change the modality. I'm coming more and more around to this last idea being the right one. Okay, I'm going to leave you with some conjectures. I'm currently in the process of proving that core programs are canonicalizing. I have some basic proof steps that show that core beta reduction and natural deduction normalization are the same. I also have some basic ideas about correct endpoint projection involving a tree-like topology. These are all works in progress. I'm an assistant professor trying to do this on my own, so it's slow. But to conclude, authorization logic is the correct propositions as types notion for choreographic programming. Recognizing this, though, requires hierarchical choreographies, and communication makes the story with beta equivalents much more complicated, but really interesting to work on. All right, thank you very much.
Thanks. Thanks again for your presentation, Andrew. I think we are open for one question.
So I may be misunderstanding something here, but the first thought I had when you started talking about beliefs was sort of inspired by the previous talk. I think, well, if you have an incorrect belief, could that correspond to some kind of failure?
Yeah, that's a really interesting question. I think the answer is yes, but I think in order to actually talk about that in a realistic way, you are going to have to do something more complicated than I'm doing in this work. But I think there's really interesting potential extensions of this work that go in that direction.
Okay, thanks again for your presentation. And next up, it's Andrew.
Yes, that's right. You don't get rid of me yet.
Yes, yes, with Masquerade Information Flow Control for choreographies.
All right. For some of you, you'll have seen a version of this talk before. I apologize if that's the case and you're bored. All right. So this is work with my student, Mike. He was supposed to give the talk to today, but his plane ended up getting canceled. He arrived at like 5 this morning. He is here. He'll be here all week. Please ask him questions, but today he is not feeling great after being in Philadelphia airport overnight. So he's not going to be able to make it today. Or he's going to be sitting in the, he's sitting in the back. So he's here, but yeah, feel free to ask him questions, but today, maybe bring them to me. It's also work with Ethan Cicchetti of the University of Wisconsin-Madison. And this talk, just like the last talk was actually about propositions as types, this talk is really about information flow security. So I'm going to start by describing what that is. So information flow security is concerned with flows, of bad flows of information. And some of those flows are direct flows. So for instance, if I have my social security number, that might be an input to a program, and it's secret. I don't want it shared with the world. So it shouldn't be shared with the public. So if I do things like just immediately output it to the public, that's probably bad. I shouldn't do that. Yeah, this is not good. We want to avoid such things. Of course, we can be a little bit more indirect. It's still considered a direct flow. So I can have some public output variable. This is a public output. It can be shared with the public. And then I can do something like this. And I've just shared a public output with the public. That's OK, right? Nothing wrong with this. I mean, I did just put my social security number in that public variable before I did this, so maybe that wasn't such a good idea either. So this is another form of direct leak. But there's another more sneaky form, which are indirect flows, which start with the same setup. I have my social security number. It's an input. I have a public output. But now I'm going to look at the first bit of my social security number. And if it's 0, I'm going to assign the constant 0 to out. And if it's 1, I'm going to assign the constant 1 to out. Hey, I'm just assigning constant variables to public outputs. What's wrong with that? I hope people see the problem. I've just used control flow to leak the first bit of my social security number. And I said I didn't want information about my social security number getting out to the public. Oops. So this brings us to the idea of non-interference. And non-interference just says secret inputs do not change public outputs. So if I have a graph like this, and I say I have some secret inputs and some public inputs, the secret inputs are not allowed to affect public outputs, but the public inputs are allowed to affect anything they want. And I have to draw a diagram that looks something like this, that says that the public things are allowed to influence secret things, but secret things aren't allowed to go down. Okay? Public here, by the way, I'm going to include public side effects here as part of my public outputs. So no using nasty side effect tricks to try to get around this. And the way we formalize this is actually by looking at 2 runs of the program with the same public inputs. And we say, well, if I have the same public inputs, doesn't matter what the secret inputs are, I should have the same public outputs. And how do we actually enforce this? How do we make sure that my programs are non-interfering in this way? Well, how do we do anything in this world with type systems? Yay, types. And type systems, our type system looks like this. And this looks somewhat confusing. I mean, there's a lot more here than you're used to. But most of it is really just the ordinary type system. We've only added a couple of extra components. The first component we've added is this information flow label L. And L here is drawn from an arbitrary preorder. So it represents a security policy. And we say that L flows to L prime. I'm going to pronounce this flows to, this square subset symbol, means that information labeled L is allowed to influence information labeled L prime. So public flows to private, but not the other way around. We also have this program counter label. This program counter label, it's drawn from the same preorder as L. It's also an information flow label. But what it does, what its job is to track the sensitivity of the control flow. So how do we use this sort of type system to get rid of flows? Well, if you have a direct flow, you have public to secret, num public to secret to unit, and num secret, you might ask, can I use SSIN as a input to output public? And the answer, if you don't have anything here, is obviously no, there are different types. But okay, we can use our information flow for subtyping. And I still can't do anything here because the flows go in the wrong direction. So that's good, actually. I want to not be able to do this. Obviously, same story here. I don't need anything extra. But what about for the indirect flows? What do I do? Well, this is where that program counter comes into play. Because what I can do is I can say, I'm going to start type checking in public. Because there's no constraints yet from the control flow. But when I go inside of the if, I'm going to taint my PC with the label of the thing I'm checking. So here, the label of my SSN. Why? Because at this point, my control flow can leak information about the SSN. And then we're going to say, look, you're not allowed to do a public assignment like this in a tainted context. So that gets rid of those nasty effect attacks I was talking about earlier. You can't use effects to get out of me here. So all of this works really well for single-threaded programs. There's been a lot of work on this for single-threaded programs, including distributed single-threaded programs, which I think is kind of neat. But when you get to multi-threading, things start to break. Let's see why. Let's imagine I have thread 1, and what it does is it looks at the first bit of my social security number, and it's going to check if it's 0, it's going to activate T2, and then it's going to activate T3. Otherwise, it's going to do the other way around. And when I say activate here, all I mean is we're going to send some uninteresting message and wait for a response and then throw it away. Right? So we're doing nothing interesting here in some sense. And then what threads 2 and 3 are going to do is they're going to wait for this uninteresting message. I have this activate form, which just means wait for unit, throw it away, do the thing inside the body, then send unit back. Right? And what they're going to do is they're just going to output their name to the public. But now a public observer can look at this, and by seeing the order in which these two things occur, they know the first bit of my social security number again. The big problem is that if you analyze these programs separately, this program looks like it's doing nothing interesting. I'm sending some unit messages. Who cares about unit messages? Over here, however, I have no information about the control flow that led me to this point. So I can't detect that I'm actually doing a bad thing by outputting to the public here. And this leads to an uncaught leak. So we're trying to solve this with Masquerade. Masquerade is a choreographic language. It's basically pirouette, where we've added information flow labels. That's pretty much it. And what's shocking to us is that it seems to work. We have all of the nice functional things, higher order functions, recursion, etc. I'm going to skip past this slide because I went through this slide in my last talk, and you all saw it. And the key insight here is that by putting everything in a global system, we have more powerful analysis. So now I'm going to have activates, and this is activation from a global point of view. So this is T1 sending a message to T2, T2 doing the body, T2 sending the message back. But now, when I try to analyze this program, I know what context I was in. So I can just use my standard PC manipulation tricks to establish non-interference. Yay! Now, this works as long as the local language, remember pirouette has a local language that represents the local programs, as long as that's non-interfering. And of course, if the local language allows programs like this, all hope is lost. You're not going to be able to do anything. Our conjecture, therefore, is that, well, if you have a non-interfering, if you have well-typed local programs being non-interfering, then so is Masquerade. But what if we want to do more? What if we actually want to leak information? And you might ask, why would we want to leak information? Well, imagine that I take in a username and a guess for a password. I can look up the username's actual password in a database table. I then ask, are they the same? Is the password actually the correct password? And if they are, I allow them in. And if they're not, I don't. Non-interference says this is broken, but I say this is good security. Not bad. So what do you do? Well, you start reaching for a more subtle policy than non-interference. And in the literature, there's a myriad of declassification policies that say you're allowed to leak information, but only in a controlled way. And almost all of them compose with non-interference. What that means is if I take a policy, a program that satisfies a policy P in a non-interfering context, then the resulting program still has policy P. And that means that Masquerade should be able to preserve declassifications with an appropriate local language. And so our actual conjecture, again, this is a work in progress, so we're still working on proving this, is that if the local language has a security guarantee G, which composes with non-interference, then Masquerade, with that language as its local language, has that same guarantee G. And then we get non-interference as a corollary. Like I said, this is a work in progress. We actually have a cock model of Masquerade we've been working on. We have the syntax and type system. We have progress and preservation proofs. We're currently working on a logical relations argument to establish global non-interference. We plan to use a formal trace argument to establish non-interference after projection, which is going to be a really powerful thing, really interesting to talk about. The basic form of that is, look, if projecting the global trace gives a local trace, so we can prove that if the global trace is non-interfering, which we know it is by the logical relations argument, then the local traces, when run together, must be non-interfering. And with that, I think I have some time for questions.
Thank you very much. Are there any questions? Yep.
I can go. Thank you. Do you have any ideas on timing attacks for a password?
Timing attacks. So timing attacks are really hard to deal with in information flow. You can do them, but you end up, especially with static information flow control, where I'm making sure that this program at compile time is secure. Anything that mitigates timing attacks is really, really restrictive. This is still really useful in like cryptographic settings, and people do this with there's checkers for cryptographic constant time programming, for instance. We don't want to deal with it here because nobody wants to deal with network and timing. Oh, no, now I'm going to get a hard question.
I'm not going to give you a hard question. Similar concept, concurrent information flow languages do have notions of termination channels that are meaningful, unlike sequential ones. Mm-hmm. What is the sort of termination answer in Masquerade?
So the type system we have is currently termination insensitive because type systems that are termination sensitive are very, very restrictive. The logical relation is naturally termination sensitive. We have to do some work to break that, actually, in order to make the type system work. But it's pretty easy to give a termination sensitive semantics to Masquerade. It's just that it's going to be more restrictive than you probably want to program in for normal reasons.
That makes sense.
More of a guess than a question. Are you embedding the entire census of all parties that exist in your security lattice?
No, the security lattice is an arbitrary preorder.
But there's no concept of revealing things to the public, so how do you know if you did something bad? Because there's no public in a choreography.
So every process we do associate with a label. So I guess in that sense we have an embedding, but it's not actually an embedding. It's not required to satisfy any of the nice properties an embedding would satisfy. We just say there is some label that this process is allowed to see, and it's not allowed to see more than that. So it's not trusted to enforce more than that label.
Yeah, thanks for the talk. Just one question. So there is a bunch of work on the pi calculus where you do non-interference, basically. And so my question is, doing this at the choreography level, does it give you any advantage? Because I could also imagine, I want to use a choreography language, but then I can project, and then I could use these kind of endpoint techniques instead.
So yeah, that's a great question. So the big advantage it gives you is the ability to do static things. So if you try to do, there is work doing stuff with the PyCalculus and session types to try to do static information flow control. Stephanie Balzer and some of her team have done really excellent work here. Ferzan Dirksen and Limon Jia, I believe, are the three people in that paper. Really, really amazing work. Really, really complicated to apply and really, really restrictive. So they have to say things like, once you've sent a message, you're no longer allowed to handle any data with a level below that message in order to avoid the problem that I showed in this slide earlier. And so they're able to establish static information flow in that case, but it's super restrictive. You can do more things dynamically, but then you have the problem of dynamic checks and termination leaks. So this gives you the ability to do static things without those restrictions.
Thanks again, Andrew. So we are closing the first session of CP, and we are going to lunch. But Lindsay asked me to, well, you can say that.
Yes, if you are in the session right after lunch, let's reconvene here. So the session begins at 13:40, but if you're speaking in that session, please come at 13:30 or 1:30 p.m. For those of us who don't understand 24-hour time. And then we'll do a quick AV check at that time. So come back 10 minutes early from lunch. Thanks. All right, let's thank Andrew one last time. who's going to be telling us about probabilistic choreographic programming.
All right, so thanks, Lindsay. I have 18 minutes from now. So I'll try to be fast. So this is a joint work with Adele, who is now a postdoc at Darmstadt. And yeah, it's about using choreographic programming for modeling probabilistic systems. And so in one slide, the idea is to find a choreographic language, a high-level language for modeling some concurrent systems that is built on top of Prism. So Prism is a model checker. I'll tell you in a second what it is. And on top of Prism, there is something called the Prism language, or I don't know exactly how they call it. They call it just Prism, which is a distributed, well, concurrent language where you can write processes. And what we have done basically is to design a choreography language on top of that. And the goal of this talk actually is to show phase one of this work, where we kind of discuss the what it means actually to design a choreographic language for these probabilistic things. And this is some work that we have just, it was just presented last week at Coordination. So Prism. Prism is a probabilistic model checker. The idea is to use it for modeling probabilistic communicating systems or concurrent systems. And the idea is it's based on the language on top of Prism is some language that is some sort of CSP. So if you know CSP, but it's a declarative probabilistic CSP. I will tell you in a minute what that means. So here I have an example. So Prism has modules that are basically processes, if you want. And what happens is that you have a sequence of instructions. And instructions, they're called commands. And they have this kind of format here. So you have a label. Here I call it beta, which is used basically by different modules to synchronize. So it's like a channel in the pi calculus, but it's as something where more than two processes modules can synchronize. Then you have a command also as a guard, which is basically a query on the state, and that's a query on the global state. So you can make queries on local variables, but also on variables at other locations. And then you have this thing here, which is a rate or a probability. And the idea is that you want to execute this particular command with some probability mu or rates. It depends on the kind of model that you're using. And then finally, you have the state update. If you're going to execute this command, then you're going to update the state with some assignment here. So it's very simple. But the idea is that, I mean, there are some advantages. It's a declarative approach. And like all declarative approach, they are easy to extend. So if you're modeling something, you want to add some extra feature, you just throw in some extra things into your model. However, it can be really hard to predict what the program is doing. I mean, and this goes back also to what Fabrizio was saying this morning. If you want to understand what a concurrent program with many threads or processes running in parallel, you kind of have to reconstruct what the execution was, because that's the way we think about it. So there is a high risk of modeling something else that was intended. So, and the question we asked ourselves when Adele actually came to visit me here in Copenhagen was can we actually try to model these concurrent probabilistic systems that they do in Prism? There's a huge, on their website, actually, there is a massive amount of use cases where they use it. And there are applications all over different areas. And then we asked ourselves, actually, can we have a choreographic program, a choreographic language that we can build on top of it so that we can write programs that then they can compile into Prism. So I'll go back to the thing. Well, I don't have it. But so that you can compile to Prism and then model check. Or are there other advantages that choreographic programming could give us? So just to give you an example, so we did actually design this language. And just to give you an example, the program I showed you before that I have no idea what it does if I look up there. But what it basically does, there is two modules, two roles, or whatever you want to call them. And you have this sequence of interactions, basically. The user communicates with this checkout module. And then with some probability, it does something, or with some other probability, does something else. I mean, it's very simple. So it's just a sequence of interactions. And already here you can see that the readability is much, 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 much better. And the goal of this work was just to see if we could improve the readability and see what impact it has also on the performance that Prism does. What we did more into detail, we defined we did the theory first, and then we actually implemented. And what you expect, we did the standard homework, which was define first the language within its semantics for the choreographic language that we were going to also implement. Give a semantics to Prism, which is there in some informal way, but we kind of formalized a little bit better, and then defined a proper notion of projection, proved it correct, and then implemented it. Now, the language, at least the calculus, is very simple. It just has one interaction primitives. So here you have a synchronization between n+1 modules. I'm going to call them modules from now on because that's the way they're called in Prism. So you have it's synchronous. That's the way Prism works. And so you can have a synchronization between many, not only two, as we saw maybe today only. And then you can have branching. And the idea is that you have a certain number of branches with some probability lambda I. So if you're using probabilities here, you want that the sum of these lambda i's, lambda j's, is equal to 1. If you're using rates, then it doesn't really matter. And then what you have for each branch that you may choose probabilistically, you will do an update to the state of each module. Okay? There is an if-then-else construct, which is located, and some recursion. These are the updates. I'm not going to go into details, but they are like the ones you do in Prism. And here are some examples. So for instance, here there is a synchronization between P, Q, and R. And with probability 0.3, P, so these variables are located. And here implicitly, I'm assuming that X is located at P, Y is located at Q, and Z is located at R. And you do some distributed state update, right? And with probability 0.7, then there is only P who updates X to that value, okay? There is some more. I'm not going to go more into details, but you can also do recursion. And what we did then, you can define a semantics, which is very standard semantics, where you update the state. However, there is some extra thing whenever you select some particular branch, then that transition has some probability or rate, lambda j. So in these cases, obviously, the probability is 1 because you have no choice. To give you an example, then if we take, for instance, this choreography here, there is a synchronization between P and Q with rate lambda 1. So there is only one option. So with rates, the sum doesn't have to be equal to 1. And there is this update. And then there will be something else. And then you can construct from the semantics actually a Markov chain. Okay? So if you're using rates, you will have a CTMC. If you're using probabilities, you will have a DTMC, sorry, deterministic transitions. Yeah. Right, so I have more examples here, which I'm not going to go through. But then what we did, we tried to do the same work for Prism. And in Prism case, you have networks, which are collections of modules. They're called modules. And each module has a set of commands. Okay? And commands, as I showed you in the example in the beginning, there it was the real syntax of Prism. Here there is some abstract version of that, but it's basically the same. You have some label alpha where you want to synchronize on. You have a guard, as you remember I showed that, and then you have a certain number of branches, and each branch, probabilistic branch, does an update to the state. Semantics for Prism is a little bit more complicated, and it's kind of nasty because these synchronization labels are sort of collectors in the sense that if you have a system you're modeling with all these people in this room, each of you is a module, and I say A, label A, then the semantics of CSP also works like this. Then everyone who can do an A has to do that A as well, has to synchronize as well. So it's kind of forcing everyone to do that synchronization. So what you have to do is somehow collect all the labels and then do a synchronization over the labels. The interesting thing is that when I collect all those modules that can do an A together, then what I have to do the end of their guards. So I construct a new command, but then also I need to take the product of all the possible probabilities. This is very standard. Actually, you can model this as a matrix. But it becomes interesting when you have to build a Markov chain out of this, because it can become very complex, actually building up all the possible combinations. And what happened is that then the semantics is still a transition between states. And what you want to do is to define a transition from some state S to some state S prime. You need to collect all those possible commands that allow you to do that transition. So you take the probability and then you sum all the probabilities. And then you need to normalize, because sometimes the sum is not equal to 1 if you have many of those. To tell a long story short, you can basically build out of a system in Prism, you can build a Markov chain. And this is what the Prism model checker does. It takes a program in Prism, and it runs something like this, and it constructs a Markov chain. So here I have an example. Without going into details, I have these two modules, and out of these two modules, I can build a Markov chain, right? And now the question is, I showed you some choreographies, and I showed you Prism, and I would like to have basically take the choreographies and compile them into Prism, and then show you that the Markov chains that I build in the two worlds, they are somehow equivalent. Here is the picture. So the way we do it is that basically now you have you don't have a sequencing basically in Prism, right? I mean, if you have to do a standard projection, what you usually would do, you just use, if the choreography tells you do this and then do this and then do that, then you will use the sequencing operator or the semicolon or some sort of operator like that, like in an imperative language, that it would allow you to execute things in the right order. You don't have that in Prism because you have only a list of commands, right? And you just need to play with labels and state. It's a sort of hack, if you want, the way you project a choreography. But you want to play with states to somehow simulate the behavior that is said in the choreography. And what we do is basically we do some annotation. We annotate all the interactions that are in the choreography with some label. And since it's a finite program, you can just find always a finite annotation to the choreography. And then we use it for constructing the projection. And before I run out of time, I will briefly show you this. For example, for this choreography here, what you do is that here you will have to do a synchronization between P, Q, and R. So you will use this label L as a label this should be L1, I'm sorry, as a label in Prism, and then you will basically encode this. And then you will use the state. So this is the state that is updated by the choreography, and you leave it as it is. But then you have some extra working variables for keeping track of where you are in the choreography, basically. This is the definition of the projection. There is a slight difference between projecting a CTMC and projecting a DTMC. And this is just for information that you can go and look in the paper. We have some correspondence. So basically, we show that if you have a choreography that is nice, let's say, under some conditions, then basically you have that the Markov chain constructed by the choreography is behaving, it modifies the state the same way that it does, the projection does. We have implemented this. And what we did was basically we implemented a language. So there is a parser, if you want. And then what the tool does, it generates Prim's code. And then what you do is that you can use the Prim's code to feed it to the Prim's model checker, and it will check some properties for you. We have actually done some interesting protocols. There is a paper where they model in Prism Bitcoin protocol, a proof of work, and we have remodeled it as a choreography, and it's much more concise. Here is, okay, this is not very readable the way I put it in the slide. I'm sorry, but the version in Prism is like you have one page like this for each module. So it's really difficult to reconstruct what the thing does. And we also did some benchmarking, basically. We showed that because the projection, of course, is not like the ad hoc modeling that you've done. So there could be some overhead introduced by the projection. But roughly, they behave the same. And then I'll just conclude. Yeah, I still have the time. What's next? So this is still a very toy language. And we have realized that in some cases, when we want to model some examples that you find actually in the Prism website, we are missing some operations. One thing, for instance, I was talking just before lunch with some people, is that you may have, there are some examples where you want to model probabilistic choices that are local. So for example, let's say that it's me, Marco, and Fabrizio. Sorry. And we all want to throw a dice, right? And then you want to write a choreography that does that based on the outcome of the dice. Yes, I'm finishing. Then modeling that directly in this language would be very complicated because you would have to list all the possible executions. But there are some language constructs that you can add to the language to do that. But maybe the most important thing that I want to focus on, and then I'll promise I'll stop, is can we use choreographies for improving the performance of Prism? And the idea is that from the semantics of the choreographies that I showed you, you can actually directly generate these Markov chains that are directly fed into the Prism model checker. And when it comes to reconstructing interactions, we can be much faster because doing the choreography, you're already automatically giving what the synchronization should be. And then I'll stop, although I'm late. Sorry.
We have time for one question.
Thanks, Marco. You said that you have recursion.
Yeah.
And if you have recursion, how do you have like finite amount of interactions that you need in order to kind of generate the sequence or other things? I didn't understand exactly.
So the number of commands still it's regular. The programs are a regular language, so you can always write it in a finite number of states. However, since you can do state updates, then the Markov chain would be infinite. But that's the case also with Prism.
Okay. And also another point is, since you have like now probabilities, then there are some paths that probably will have like a negligible or go
Say it
to
again?
If you have recursion and then probability, there are some paths that probably will go to probability 0 in the long run. How do you treat them? Are they equivalent basically to potentially even like a program that has deadlock in it? Or so imagine that you have a program that has deadlock, but the probability to reach it is 0.
But you cannot model that with a choreography. So
Yeah.
you can do that in Prism.
Okay. So potentially, it could be nice also for if you're thinking about extraction or other reusability, potentially to even enrich your program to have like a primitive for saying deadlock.
In general, this is not decidable. So yes, but this is a good point. Thank you. Yeah. So
Let's thank Marco and once again.
Thank you.
Sì.
All right, and next up, Matteo is going to be telling us about a function as a service choreographic programming language.
So, okay, this works. Nice.
Stay on the stage.
Here?
Yeah.
Okay.
That's where the camera is.
Oh. Okay. Let's not die here. Okay. Hello, everyone. So, what I'm presenting today is a very early draft for a proposal for a choreographic programming language tailored to the realm of function as a service. This is part of ongoing research work done by me, Giuseppe De Palma, Saverio De Lorenzo, Jacopo Mauro, and Gianluigi Zavataro, who is not here today. Now, first of all, a bit of context. What is function as a service? Basically, it's the main subset of what is known as serverless computing. And like everything related to serverless computing, the main principle behind it is that we want the user to be as removed and as oblivious as possible to every concern, especially when it comes to
All right, next up, you've heard of algebraic data types. Now let's hear about algebraic data places.
Okay, so thanks. Hello, everyone. I'm Pascal. And this work on exploring algebraic placement and multi-party languages is joint work with George and Guido from the University in St. Gallen, who are also here in the room. Okay, so in our group, we have been working on multi-tier languages quite a lot. So in multi-tier languages, you can develop functionalities that span multiple tiers within the same compilation unit and using the same programming language. And then the compiler will take care of generating the code for the different tiers and the communication between them automatically. So this is kind of similar to endpoint projection in choreographies. And then tiers can be a client, a server, a database, or any other network node or network service. So apparently, multi-tier programming is quite a close cousin to choreographic programming, where you essentially compose concurrent processes, right, that interact with each other. And this is kind of similar to how you specify the interaction of different tiers or components or parties in multi-tier programming. So these two approaches, they have a very similar core idea in the sense that they let developers reason about different parties and how they interact. And so while we did our work here in the context of multi-tier programming, we believe that it applies equally to all these kind of multi-party languages that share this idea of reasoning about parties and their interaction. All right, actually the insight that multi-tier programming and choreographic programming are built on some similar core ideas was developed by some people from the multi-tier community and the choreographic community, including most of which are in this room today here, and also gave a keynote. And this was published few years ago at ECOF. Okay, so let me first show to you how some of these basic ideas that we will use in this talk, how they look like in both choreographic programming and multi-tier programming. And then you can also see that although we use multi-tier languages here as an example, the ideas should transfer to choreographic languages as well. So I will use the example of a single sign-on token where a user sends a password to an SSO component, which then checks the password, and if it is correct, sends both the user and the server an access token. So in choreographic programming, so here we use Haskell as an example language. We would first define the different parties. So here the user, the SSO, and the server. And then we define the choreographic program, in which we define the interactions between these parties. So the user sends the password to the SSO. Then the SSO checks the password and generates a token. The SSO sends the token to the server, where then the server adds this token to some kind of store for verified tokens. And then finally, the SSO also sends the token to the user. All right, so what we can see here is that this program describes the interaction kind of from an objective view, where we always state which party sends which data to which other party. And now let's compare this to multi-tier programming. Here we also start with defining the different parties. We use Scala Loki as an example languages, where parties are called peers. So here we define both the parties' names and also like their architectural relation. So we say that the user and the server connect to the SSO, and the SSO connects to both the user and the server. And then we would first define a block of code that is to be executed on the user. Then this block runs another nested block on the SSO and transfers the password from the user to the SSO peer. And then the SSO checks the password, generates a token. And then it runs another nested block on the server, where the server adds the token to the store of verified token. And finally, the SSO returns the token to the user. So you can see that this program kind of describes the same interaction, but maybe from what we could call a more subjective view, where we compose sub-expressions that are executed in the context of different peers. And then by nesting them, the lexical scope determines where code is executed. All right. So if we compare both approaches, we can see that there is a bit of shift in perspective maybe, but they both describe a multi-party program in a kind of a similar way. And in particular, they both use statically defined parties to specify where code is placed. And this talk will focus on the exploration of this kind of static placement. There also has been quite a body of work on static checks to ensure safe placement, also in the context of multi-tier and choreographic languages, and also some other related approaches. Good. So our exploration of static placement started in 2018, where we explored treating static placement as part of the type system. And the idea is that similar to a type that describes what a value is, like an integer or Boolean, you can also have a placement type that states where the value is, like in the database or in the cache. And we explored this correspondence between types and places in the context of our Scala Loki multi-tier language. And I will give you a short example of how these basic places are used there. So we've already seen how we define the architectural relations of the different peers. So here we define a client that always connects to a single server, and the server that connects to multiple clients and multiple servers too. And then every client has like this message variable here. So given by the type of message, we can see that this is a string placed on the clients. And then the server can now access the messages of all the connected clients. So here hash messages is placed on the server and wants to access the message variable that is placed on the client, which means that this code like this would not compile yet because the placements do not match. What we will do is that the server would execute a remote block that specifically transfers the control flow to the client, where then the call to hash is invoked and then transfers back the result from all the clients using this as local from all construct. So the first important, more advanced feature, let's say, we ported from type systems and reinterpreted in the context of placement is a parametric polymorphism. And like polymorphic types abstract over concrete types, polymorphic placement abstract over concrete places. So this feature allowed us to implement what we call multi-tier modules. So modules encapsulate the distributed functionality, but they are generic in the peers on which this functionality is executed. So let's have an example of how such a multi-tier module could look like. Here we have an offloading module, which is defined on a master peer and a worker peer. And these peers are essentially abstract polymorphic types. So this offloading module allows offloading tasks to worker nodes. And then we have another module that implements the functionality for monitoring if workers are still reachable, for example, using heartbeat mechanism. And now let's assume that there's a third module, the task scheduler, which dispatches tasks to workers and also reschedules them when a worker is unable to provide a result. So this means that the task scheduler contains the functionalities of both the offloading module and the monitoring module. So we can just stack these modules together to combine their functionalities. And here's an excerpt of how the developer could implement those modules. You don't have to read this code in detail. What I want to point out here is that the implementation of the offloading modules contains the architecture specification, and the peers are defined as abstract types. And then the monitoring module also specifies the architecture and the functionality, and we can then simply stack those together using into a task scheduler module that combines both of the task dispatching and monitoring functionality. And the way we do this is just using mixing, composition, and trade, which then unifies the peer polymorphic types of the modules that are stacked together. All right, let me show you how this peer polymorphic module system can be used for a distributed algorithm which ensures that mutual exclusion when accessing a shared resource. So in our example, the nodes in the distributed system first elect a leader, and then the other nodes can acquire a lock for accessing a resource from the leader that either grants a lock or denies the lock. So we often have the case, like in this example, that a distributed algorithm relies on another algorithm, and to express this kind of dependency, we can specify constraints on the multi-tool modules. For example, this mutual exclusion module implements some locking functionality on instances of this polymorphic peer type node, and it requires a leader election functionality defined on the node. So the mutual exclusion module is constrained over a leader election module, and we can just stack it with a leader election algorithm. So in this case, we would stack it with this Hirschberg-Sinclair module, which is a specific leader election algorithm that requires every node to have an ID. So we stack it with a random ID implementation. And finally, we define the complete system over a ring architecture. So here we have an overview over the modules that we can use here. The brown boxes are abstract modules, violet boxes are concrete implementations. And we can see that we implemented different leader election algorithms like Yurio, Raft, Hirschberg, Sinclair, which we then can provide as modules and provide different predefined architectures. All right, so the next problem that we were looking into is dynamic placement. So far, the problem is that static placement provides strong correctness guarantees, but it does not really support very well choosing places dynamically. Although dynamic placement is very crucial in a lot of use cases like caching, geo-replication, and so on. So the way that dynamic placement is implemented today is using entirely dynamic checks often. A popular technique is actually to check the string representation of URLs. So in this example here, we check whether a URL starts with HTTP to determine whether it's placed locally or remotely. And we found a lot of projects that do something like this. And obviously, this approach gives up on static guarantees completely. So all issues will manifest as runtime errors and maybe program crashes. So our key insight in this work was that sometimes essentially, as we know them from type systems, they capture this kind of dynamic choice. So some placements capture dynamic placement. So this was the next correspondence we could draw from type systems and reinterpret this in the placement context. And this is quite recent work published in last year's OOPSLA. So in our Scala Loci language, we represent dynamic placement using a first-class placed union type. So this type that we see here represents some data placed on a peer P or on a peer Q. And then this represents like placement that is statically uncertain, but is determined at runtime. And we can then eliminate some requirements for some runtime checks if we know from the architecture that the remote access is safe anyway. So union types can be introduced by subsumption. So in this case, for example, we create a new place value on the cache, and then we widen its type to say that it's placed either on the cache or on the database. And then in the end, placement can depend on the dynamic choice of where the data is actually created or where it is retrieved from. They are eliminated by splitting on the possible choices of their placement, very similar to some types. So in the example, we have a branch that handles the placement on the database and one branch that handles the placement on the cache. So the obvious question is, well, what's next here? What will be the next entry in this table of correspondence between placement and types? And now that we have sums, one could ask, well, what is the interpretation of products as placement? And in this work here, we kind of found that we can interpret products as sharing or replication of data. So in Scala Loci, such placements could be represented by an intersection type, which means that the value is available on all the stated peers. So we can eliminate then intersections by just selecting one specific peer that we want to access, essentially projecting the value to the value that is placed on this given peer. All right. So what's really interesting at this point is that with sums and products, we essentially now have an algebra of placements. And this means that there are certain algebraic laws that hold for placement types. And in particular, union and intersection placements form a distributive lattice with the usual laws of associativity, commutativity, and distributivity, as you can see here. So n distributes over or distributes over n. And well, this sounds really nice, but how can we use this? So let's consider the following example. So here we have some data that is placed on a database and the client, or on a client and the cache. So if we want to process this value somehow, the shape of its type kind of demands that we perform a case split on the union type, because it's the outermost type is a union, right? So what we would do is need that after the split in the first case, we can then project the value to the client and retrieve the value from the client to process it further. But also in the second case, we want to project the value to the client peer. So this means we have to kind of duplicate this logic of projecting and retrieving the value in both cases. Instead, what we want to write is just the projection to the client peer and then access the value from that peer. And this could be possible in a type system that can reason about placement algebras. Because by using commutativity and distributivity, we can essentially factor out the client peer in the placement type, which then allows us for the projection to the client. So then in the end, all we would need to have to write is like these 2 lines of code. So this is one application of these placement algebras that we found, and for future work we are also currently thinking about optimizations for placement and access based on applying some algebraic laws. So what could the smart compiler do if we know these laws hold? Which at this point I will just leave this question to you. So let me conclude this talk by going back to our table of correspondence between type system features and their interpretation in the placement context. So here we are working on exploring this correspondence in a more systematic way, which so far resulted in a couple of known type system ideas to be also useful when interpreted as placements, and which has recently let us discover this kind of algebra on placements. All right, that's it from my side. Thanks for your attention, and I'm open for questions.
Check. Good talk, really good talk. So one question I have is, I suppose you implement all this in Scala?
Yes.
And I'm curious to learn how hard it is to, encode this fancy type system using Scala. Do you have to use any tricks or?
Right. Maybe we can take this offline because this will take a lot of time to explain.
So it's not easy.
But no. The thing is, so Scala has a very expressive type system. You can encode a lot of stuff, which is not trivial, but doable, let's say.
Okay.
But in the end, we also use quite some amount of codes of macros that kind of transfer ISTs after the fact. So we kind of hook into the compilation pipeline also to do this. So on the technical side, it is a bit involved. So if you want to hear more details about this, I'm happy to talk about this.
Okay, sure. Another question.
Yes, of course.
So, so here you have the connection between a traditional type system and placement type system.
Right.
I guess another connection I can think of, which is missing here, is recursive types.
Yes.
Have you thought anything about that?
Yes. This is a very, very good point. And I believe this is also something that I want to stimulate with this table. Look a bit into what other type system features are there and how they could interpret the placement types, like recursive types that you mentioned, which would be very interesting. If you have an idea what they would mean, I'm also happy to hear it. We are also thinking about things like this, but so far, I don't have a definite answer, so to say, what they are.
We can definitely talk about this offline,
yes.
but one thing I can think of that use recursive type is maybe surfaces. I don't know. Something you want to run
Could be,
continuously.
yes, yes. But yeah, definitely an interesting question.
Other questions?
So you're using products at the placement level to represent shared data.
Yes, kind of.
Can you do the same thing with computations? Can you share computations in the same way?
Well, we could at least express that like the same kind of computation is placed on two different peers, at least at the typing aspect, so to say. So you have a computation that gets the same types of arguments, produces the same type of data, and this is somehow placed on multiple peers, but it doesn't really say something about what the computation itself does, so to say, yes.
Thanks for the great presentation. So you are, this is, I think, the fourth proposal that I see thinking about this kind of stuff.
Right.
The other three, though, are in more choreographic programming. And a big difference I see is that if we were to do something like this in choreographies, we would be able to express data structures that say something like, okay, this part of the data, these two participants agree on, and then there's another part of the data where these other participants agree on. Can we express anything like this in here?
What do you exactly mean by the agree on?
That it's replicated. Like we have a pair where the first element is replicated across A and B, and the second element is replicated across C and D.
Yes, I believe we can express something like this. At least, again, the typing aspect, that there is a data of this type in the two different peers, yes, sure.
Let's thank Pascal one more time. And next, we will have Dan, who's going to be telling us about the essence of choreographic programming.
No, that's for you to decide.
Okay.
This is a
Hello. My name is Mako Bates. My advisor, Joe Neer, at the University of Vermont in the United States, started working on choreographic programming a little over a year ago as a tangent to some cryptography stuff we were doing. We recently formalized a language, He Lambda Small, which features multiply located values. So that's what I'm talking about today. I'm going to try and convince you guys of three things, and I think some of them are going to be really easy. So for example, choreographic languages feature located values. It makes total sense for located values to be located in more than one place. Having multiply located values in your language will help with management of knowledge of choice. And then that's all you need. That is a knowledge of choice strategy in and of itself, and it's just as good as other existing knowledge of choice strategies. I'm going to hold on to the asterisk there for a while, but we will get to it. So here's the paper. You can read it on arXiv. It formalizes He Lambda Small, which is a minimalist lambda calculus for choreographies. We prove the normal by simulation and deadlock freedom. Check that out. But making sure we're all on the same page, what's a multiply located value? So located values, either at the term level or at the type level, get annotated with some party who owns them and is guaranteed to know them. Similarly, a multiply located value is annotated by one or more parties who know them. So on the bottom line here, x is an integer, it's 5, there's only one of it, but both Agnes and Carl know x. We can make that a little bit more formal by talking about endpoint projection. So with a singly located value, it's got some party, in this case P2, that it's annotated with, and it will project to itself or not, depending on whether the party to which you're projecting is P2. A multiply located value works the same way, except that it's annotated with a list or a set, PS, and during endpoint projection, you're checking for set membership or list membership instead of equality. So that's how you interpret and represent multiply located values, but then how do they actually arise in computation? So one option is to replace your communication operator with a sharing operator. So x is an integer known to Agnes and Emil. Agnes shares x with Carl. Now x is an integer known to Agnes and Emil and Carl. Our earlier cryptography-focused stuff worked this way. Whether or not it makes sense for a variable to change its type during execution of a program depends on your computational model and the whole rest of your context. So another option is to upgrade from communication to multicast. So again, x is known to Agnes and Emil, but now Agnes is sending as a single action x to Carl and Frida. We bind that computation to y. Y is an integer known to Carl and Frida. That's how Helium-Small works. It's the simplest system we could put together. But you can combine those. So again, Agnes sends x to Carl and Frida, but now we do set union, and y is an integer known to Agnes and Emil and Carl and Frida. In order for the rest of the language to work out nicely, you're going to need to support subset-based subtyping, which is a good idea. We should do that. But maybe we need to motivate some of this. So what are multiply located values good for? Well, one, knowledge of choice. I'm going to spend the entire rest of the talk talking about that. But they also help improve things in other ways. They make your code a little bit more flexible, because if Agnes and Carl both know y, and something needs to be done with y, then Agnes can do it, and Carl can do it. They also make your code a bit more concise. So on the second to last line of this example here, we have addition of x and y. It doesn't say who does that. X and y are both known to both Agnes and Carl, so Agnes and Carl will both do the addition, and we end up with z is an integer known to Agnes and Carl. When we were writing Helium-Small, when we wrote We Know I Know You Know, we didn't even bother naming this, but then we wanted to include it in the API for multi-core, so we had to give it a name. We ended up with congruent computation, because Agnes and Carl aren't just computing in parallel, they're actually computing the same z. It's more than parallel, it's congruent. I realize I haven't told you guys about multi-core yet. Multi-core, census polymorphic choreographic programming with multiple located values. So Helium-Small was an abstract lambda calculus about which we have some nice proofs. Multi-core is a Haskell library you can use to write software. Roughly speaking, what we did is we rebuilt Hascore, thank you again, implementing the stuff I'm talking about here, pulling out some other tricks so that you can do this stuff in a way that works out nicely in Haskell's type system and have Haskell's type system actually help you with it. And then we took it a step further so we could do census polymorphism. So several languages so far have done location polymorphism, where you have a role that can be fulfilled by different identities in different contexts. If you extend that to sets, where the whole set, including its cardinality, is polymorphic, then the most interesting application of that is applying it to the census, the annotation or the context on a choreography of who's actually present to participate. This lets multi-core express choreographies that are polymorphic on the number of participants. However, let's go back to Helium-Small. So x is an integer known to Agnes and Carl. Agnes can use x, Carl can use x. What can they use it for? Well, they could use it as a branch guard. But as I was talking about with congruent computation, they can use x together, so they can branch together. This is knowledge of choice. Making sure we're all on the same page. In a choreography, you often need to make sure and perform some communication so that different parties can follow the same path through control flow. That's the knowledge of choice problem. There's different strategies. I'm going to only talk about 2 others besides this today. I don't think anyone will accuse me of softballing that. They're very good strategies up there. Yeah. So on the left here, we have a select-based choreography. Agnes knows some integer x, and then down at the very bottom, she and Carl may or may not, depending on the value, need to perform some subcomputation on it. But when they get there, it needs to be located at Carl. So the very first thing Agnes does is she sends x to Carl, call his copy y, then she branches. But in order for endpoint projection to work out, in order for this to be well formed, she also needs to then tell Carl which branch she's in using these select statements. With multiply located values, we don't need to do that. When Agnes sends X to Carl, she knows the result of that computation. We make that explicit by including her as a recipient. There's no extra communication cost overhead for that. But now, they can both branch on Y, and either they do it or they don't without any further overhead. So that's how it improves your knowledge of choice management, and that's actually all you need. Helium small doesn't have select statements. There's no merging process during endpoint projection. All well-typed helium small programs are well-formed. Not everyone here thinks that type systems are the only static analyzer. They're not the only static analyzer. But this is a big deal for library level implementations especially. So multi-core and has-core, endpoint projection happens at runtime. So if you're throwing errors during endpoint projection, that's a problem. In terms of how you actually use this strategy, well, you just don't inform your peers which branch you took. Instead, you send them the guard before branching. It will often work out that they already have it, or they already have what they need to compute it. Side-by-side comparison, how does multi-local and multicast paradigm stack up to select and merge? Well, your communications are all data. If I send you something as a branch guard, you now have a piece of data, a value that you can do computations on. Also, if you have knowledge of choice, you can use that as many times as you want in sequential branches. On the flip side, if you're doing merging of your branches, and that's actually doing anything to the resultant code, that means that you have duplicated code. But let's pull in the asterisk from the very beginning. So what was that about? There will be times when you don't want to, or possibly even can't, send the entire branch guard. And also, if you have a deep nesting of branches, you might not want to send all of the branch guards. That's very easy to do in a select and merge paradigm. We're going to look at what it looks like with multiply located values. It's not quite as clean. But an example, so this is an example of sequential branching. We have Alice, Bob, and Carol. In the middle, let response equals. That's Carol acting as a server. She gets a query from Alice, and then she sends the response to Alice and Bob. But before that can happen, Alice and Bob branch together on a shared variable choice to decide whether to use Alice's query or a query that Bob sends her. And then after they get the response back, they have to branch again so that the right party can call the respective handler on that response. But those two branches are on the same variable choice. So whatever communication overhead was involved in creating choice only gets paid once. Sequential branches are free. So predicate transformers. I haven't met Jongmans or Van de Bos, so hopefully that's the correct pronunciation of their names. They put this forth a couple of years. In their system, when you have a case expression, there's per party branch guards, and then a static analyzer goes through, uses predicate transformers on the semantics of your program to guarantee that all such decisions are made unanimously. It's a great system. It works out to completely subsume the knowledge of choice strategy of helium to small, but I'm pretty sure that in terms of expressive power, they're equivalent. So most of the time, any per party branching is going to just already be congruent. You just wrote it out multiple times. And then the static analysis of helium to small is much more lightweight than the predicate transformer system. And you don't have to write things out for each party. There will be cases where the expressions aren't already congruent. I'm pretty sure. I haven't written out proof yet, but I'm pretty sure there will always be a foundation of shared knowledge from which you can build a congruent expression to replace the per party guards. So focusing on select and merge, it's the multi-local, multicast system is just as good. Specifically, I'm speaking in terms of communication efficiency. How much data do the different parties need to send over the wire to each other in order to accomplish some desired behavior? Now, core lambda is able to express these things called distributed choice types, using which any program you can express in helium to small, you can express in core lambda. Let's deal with the asterisks right away. Neither core nor lambda nor helium to small are the final word in the paradigms that I'm using them as examples of. So polycore lambda can do location polymorphism. If that can be extended to location set polymorphism in the style of multicore, that's a big deal. I can't suggest how to do that right now, so maybe somebody else can. But is multicast and multilocal just as good? Yes. We have another star, we have a dagger, but yes, it is. If your branches can be merged, then you can reorganize. Then you could also reorganize them into sequential case expressions. Any common behavior on the part of a party who doesn't have knowledge of choice can be expressed in the middle, in between sequential branches. Your select statements are just going to be adding, or well, they're going to be data communication so that you can add parties to the subsequent branches. But there will be cases where in order to write your program optimally in helium small, you have to have dead branches. Also, helium small represents data values in a sort of embedded mini language, which has its limitations. There are certain structures of data that it can't express, so presumably there are subsequent behaviors that it can't express. I don't have an example. So I have tons of time left. We're going to take lots of time on the last example because I want to look at why we get dead branches. I want to solve these problems. I think I know how to solve them. I have some ideas that aren't quite mature. I also kind of suspect that Maxime has already solved them. So let's look at an example of why helium small ends up with dead branches. So this is, I believe, a completely valid helium small program. Yeah, I'm not missing anything. So at the very beginning, Frida has some value. It's either an annoyingly large list or an annoyingly large matrix. Depending which it is, some handler sub-choreography needs to get called on it involving both Frida and Emil. So they're going to have to branch. But Frida does not want to send the entire value because it's too big. So first, she branches to build this variable guard, which is basically just a Boolean encoding whether her value is a left or a right. She sends that, so now Frida and Emil can both branch on guard. We'll assume for the moment that they end up in the left-hand side list. So they're in that branch. They want to call handle list on list. But in order to get a list out of the sum type that Frida has, she has to branch again. We know which branch she's going to end up in. She's going to end up in the left one. But we have to put something on the right-hand side. I put undefined. Helium small is a finite language, so you could always put a default of some sort in there. Or you could update the language so that you have partial matching, partial pattern matching. But from an engineering perspective, those are all bad options. We need to do better than this. And it seems like today we're collecting a whole bunch of ideas for how to do better than this. So those are some of the directions that we're going from here. Give your languages multiply located values. They're great. Read the papers. In particular, I'm going to be humble and say, I want you all to read multicore and tell me what I did wrong, because I'm really excited to hear about that. And stay tuned for more.
All right, there is time for a couple of questions.
Thank you for the very nice talk. I'm a little bit curious as to whether you've thought about applications of this to things like consensus at all, where somehow together a group of agents have to compute some value that they all want to agree on. Do you think that that would look a lot like what you have, or would you have to do something extra on top of it in order to actually express the fact that this arose from consensus rather than from just somebody deciding and sending out the message?
So showing that people start with nothing in common and all arrive at the same thing. The honest answer is I don't know, because I haven't opened up consensus protocols to see how they actually work. I know that being able to make them a little bit irrespective of the exact number of participants, is going to be helpful, especially like we would love to model dropout, for example. So in that sense, multi-core is a really important step, we think. As for whether or not congruent computation is going to help us with this, honestly, I just don't know what it is that we're trying to do.
Yes, also thanks for the very great talk. Since you talked about multi-core and also multiple values located at multiple locations, have you thought about values located at either a location or a different location? Because that seems like similar to the distributed lattice we had before.
Yeah, so a value located at either a location or another location, nothing we've written right now represents that specifically. What we do have in multi-core is what we're calling faceted values, where Agnes and Frida both know an integer, but it's not necessarily the same integer. And we would like them to be able to do stuff in parallel with that. Combining that with choices, with like an either type or a sum type, would get you the same thing, but whether or not that'd be an elegant way of getting the guarantees you want out, maybe not.
Okay, thank you, but multi-core looks very interesting. I'll have a look at that.
All right, let's thank our speaker once more. And we now have a break. So let's reconvene for the last session, I think in 30 minutes. Let me double check.
Okay. Ready?
Yeah,
Go.
I think so.
So, welcome everybody to the last session, unfortunately. But we're going to have a series of talk about choreographies, library level choreographies and embeddings. We're starting with Sean, who's going to present Chorus, or Chorus. Chorus.
All right, so can everyone hear me okay? Okay, so hello. So today I will talk about Chorus, which is a Rust library for doing choreographic programming. My name is Shun Kashiba, and this is a joint work with my advisor, Lindsay Cooper at UC Santa Cruz. So this is a choreographic programming workshop, so I assume everyone here is familiar with the idea of choreographic programming. I am interested in doing choreographic programming at the library level. And by which I mean we express choreographies as programs in an existing host programming language. And this is as opposed to choreographic programming languages like being a standalone and has its own syntax and semantics. Library level choreographic programming enjoys the same advantages to embedded domain specific languages. So users don't need to learn new syntax. It can be installed just like any other host language library. It works well with existing host language program. And you can use any host language developer tools like IDEs and debuggers. Haskell was the first to introduce the idea of library level choreographic programming. And here is a sample choreography in Haskell. So Haskell is a Haskell library. And we express choreographies as computation in this choreo monad. And inside this choreo monad, you could use choreographic operators like locally and squiggle arrow that represents communication. So Haskell brought choreographic programming to Haskell, which led me to this question of, what about other languages? Like we have a lot of programming languages. Can we do choreographic programming in those languages? And well, of course, we can do the same in any tooling complete language. But doing it right turns out to be non-trivial. And this is largely due to the fact that Haskell's design is tightly coupled with Haskell and its features around monads. So if we directly translate Haskell into a language without the do notation, basically what you would have is you simulate monads with method chain. So you have something, dot, and then blah, dots, and then blah. And that's not how you write programs in those languages. So I got interested in this question of, can we design choreographic programming library that is developer-friendly in those other languages? And Chorus is my attempt to that challenge. So it is a library in the Rust programming language. It is distributed as a cargo package, so it can be installed on any Rust project. And it implements endpoint projection as a well-known software engineering technique, dependency injection. So in this talk, I'll first talk about how to use Chorus as a user and how you can write choreographic code in Rust. Then I will discuss its implementation and especially how Chorus does endpoint projection. And finally, I will briefly talk about two Chorus-specific features, how Chorus encodes location set at the type level and choreographic enclave operator. So let's start writing a choreography in Rust. And obviously, we're going to use the bookseller protocol. So in the bookseller protocol, there are two locations. And the first thing we need is to define those locations. So here, so Chorus represents each location as a distinct type. So we define two empty structs, one called the buyer and the other called the seller. We also derive this choreography location trait so that the library can compare two locations for equality during the endpoint projection. Next, we define a choreography. So we create another empty struct called bookseller choreography, and this is going to be the choreography. And we implement this choreography trait on this empty struct. In order for something to be a choreography, you need to provide two things. First is this associated type L that represents a set of locations involved in this choreography. So in this case, we use this special macro location set to create a type-level encoding of location set that has both seller and buyer in it. Then we also need to provide this run method, and this is where we are going to write the actual choreographic code. So the first thing you need to do in this protocol is to get the title of the book that the buyer wants to purchase. And we assume the terminal environment, so we want to read a line from the standard input on the buyer location. In order to do such a local computation, we use the locally operator, which is right here. And we specify the location of the computation, which is buyer. And as the second argument, we provide the local computation as a closure. So inside this closure, we are just using the standard Rust code and reading a standard input one line. Because this closure returns a string, this locally operator returns a located string. So this is a located value. And where does it locate? It's located on the buyer. OK, so that's the first step. And the second step is to move this data on the buyer to the seller. And for that, we use this com operator. So in this line, we're saying move from buyer to seller, this title at buyer, which we just obtained. And as a result, we get located. It's still a string, but now it's located at the seller location. OK, so once we move the data, the seller will be able to access the value inside its local computation. So when you do a local computation, we provide this on object, which we call the unwrapper. And this provides a capability to unwrap a located value into normal Rust values. So inside, we can use this unwrap method and provide this title at seller. And you can get the regular Rust string out of it. And you can use it whatever you want. So in this case, we are using this get book price that might do maybe a database lookup. And it'll return integer. That's the price of the book. OK, so we can use the same com operator to send the price back to the buyer. And buyer can compare its price against their budget to see if they can actually purchase the book. OK, so now we have a decision. And this is located at the buyer. And I omitted the type, but it's located Boolean at buyer. So now we want to make a branch out of this located value. And in Chorus, to do so, we use the third choreographic operator called broadcast. So as its name suggests, it broadcasts a located value into all locations. So it's making it no longer a located value, and it just returns a regular Boolean in this case. And because it returns a regular Boolean, we could use any of the Rust built-in control flow constructs to make a branch. So in this case, we want to use the if statement. So if the buyer decides to buy the book, we can do more communication about the delivery date. And if not, we can just print the buyer cannot buy the book locally on the buyer. So this is the complete choreography in Chorus. And to execute this choreography, we need to take two more steps. The first is to define what's called transport. And transport describes how two locations should communicate with each other. Chorus provides the built-in HTTP transport. So if you provide the host name and the port number, you'll be able to use HTTP as a backend. You can also create your own custom transport, and you can use protocol of your choice as an underlying mechanism. So that's the first step. And the second step is to actually do the endpoint projection. You need to instantiate this projector object providing the transport. And you call EPP and run method and provide the choreography. So let's see how it works in action. So I am running the seller on the right and buyer on the left. And obviously, I want to buy the book Introduction to Choreographies. And it says, apparently, it's affordable. And the book will be delivered next week. Isn't that great? OK, so before I move on, I want to show one more example, which is this choreographic tic-tac-toe written in Rust. So this protocol involves two locations, player X and player O. And inside this Rust built-in loop, you can think of it as a while true. They take turns, make moves, and broadcast until the game is done. So and here is how it works. So this example has an AI mode that implements the minimax algorithm. So me on the left is competing against the AI on the right. I want to point out two things. So first, it might be hard to see on the screen, but some of the letters are shown in color. And to do that, I could just use the Rust library to print text in color. Because we're doing everything at the library level, you can use whatever Rust code in a local computation. Also, I'm not really an AI person, so I don't really memorize how to implement the minimax algorithm. GitHub Copilot was able to write code for me because obviously it's a library level, and large language models are familiar with the syntax and syntax of the Rust and also how algorithm works. So I think these illustrate the advantages of doing it at the library level. OK, so let's shift our focus to how the library is implemented, and especially how Chorus performs endpoint projection. The key observation of library level CP is that the behavior's choreographic operators change depending on the location to which you're projecting. So take locally operator, for example. It takes the location and computation. So what should this operator do? Well, it depends on the projection target. If the projection target is the same as the specified location, it should do the computation. Otherwise, this line should be treated as no op. Similarly, for com operator, if the projection target is the sender, you should do the send. If it's the receiver, you should do the receive, and no op otherwise. So behavior of these operators depending on the current projection target. And we can change the operator's behavior if we inject different implementations of choreographic operators into a choreography that's written in terms of an abstract interface. So let's get back to the bookstore choreography. And you notice that we used com and locally those choreographic operators on this ob object. And in this line, we're saying this op object implements this choreo-op trait. Or if you're familiar with Java, it's more like an interface or type class. This choreo-op trait defines the signature of these operators, but it doesn't talk about how this object will be implemented. So in this setup, doing endpoint projection more or less means to construct a concrete choreo-op object for the current projection target and invoke this run method with it. So here's a simplified version of EPP in Chorus. So this EPP and run method takes a choreography and construct what I call EPP op. And this is the specialized implementation of this choreo-op trait. In the locally operator, which is shown here, we compare the name of the specified location against the current projection target. If these two are the same, we execute the closure and wrap the return value inside this located value. Otherwise, we just return the placeholder value. So this is how EPP works in Chorus, and other operators are implemented similarly. So this endpoint projection as implemented as dependency injection is a really general technique, and it should work with any programming language that supports high-order functions. That said, Chorus does take advantage of Rust type system to provide more type-safe APIs. So in particular, as we saw earlier, Chorus has the notion of type-level location set. Each choreography must have an associated set of locations, and Chorus used that information to make sure that every location mentioned in the choreography is valid. And also when you do EPP, we also check that the transport knows how to communicate with every other location that might be mentioned in the choreography. And this is implemented using this location set macro that is internally using type-level heterogeneous lists. So here is how this might be useful. So suppose that you define this hello world choreography, and you say that the Alice and Bob are the only location you can use in this choreography. But you might make a mistake, and you accidentally use Carol inside this choreography. In Chorus, this is a type error. So if you're using Rust Analyzer or any other IDE plugins, it'll show up immediately as soon as you write this in the editor, which I think is really cool. Building on top of this is choreographic choreographic enclave operator, which offers a way to handle the knowledge of choice in a more fine-grained way. So as we saw, the broadcast operator sends the value to all locations, but not every location must know the value in all cases. If some locations are not affected by the choice, naive broadcast would add extra communication overhead, and also depending on the value being shared, there could be possible security implications. The enclave operator executes a sub-choreography only at a subset of locations, and doing broadcast inside the sub-choreography will reach only to its participants. And Chorus makes sure that the location set of the sub-choreography is indeed the subset of outer main choreography using the type-level location set. So that's about Chorus. It has more features than I can discuss today. So if you're interested in any of these features listed here, please check out the Chorus documentation or come talk to me later. I want to conclude the talk with some of the future research directions. I think library-level choreographic programming is still in its early stage, and there are a lot more research to be done from both practical and theoretical point of view. From practical point of view, I want to do large-scale evaluation and performance benchmarking, and hopefully doing so will reveal the advantages and disadvantages of this kind of approach. Also, encoding choreographic programming in a wider range of host languages with different characteristics will be interesting. So with EPPSDI, you should be able to implement choreographic programming library in your favorite language. And I want to see how the design of CP libraries will be affected by the host language features. From theoretical point of view, I'm interested in what kind of guarantees can we get out of library level CP. And also, I want to see new ideas in theoretical CP research, such as how you deal with asynchrony and fault tolerance encoded at the library level. OK, so that's about it. So I presented Chorus, which is a library-level choreographic programming implemented in the Rust language. So here's a link to the GitHub repo, which also has a link to the documentation. It would be great if you could leave a star on the GitHub. All right, thank you so much. That's it.
Thanks, Shen, for the interesting talk. I think we have time for a couple of questions. Let me run.
Just to connect also to your future work, what happens if so you are using a COM that is synchronous, so you are blocking the sender?
Exactly.
And what will happen if you are a mistake there? And currently, what do you think a programmer should do to handle communications errors?
Communication errors?
Yes.
Yeah, so we kind of assume there are no communication errors. So we provide basically no way of handling it. I don't know, but I feel like handling errors is difficult in choreographic programming in general. So I don't have really a good answer to that. But I would love to see how what kind of approach there are and how we can encode that at the library level.
Thanks very much. This was a really interesting talk.
Thank you.
You have higher order choreographies, so I assume you have some way of being able to compose these. But with these type level location sets,
right.
When you do a broadcast, you're broadcasting to the locations in the set of the currently defined choreography.
Correct.
When you compose choreographies, does that broadcast now change to be, say, the union of the two, or how does that work?
Yeah, so when you compose choreographies, right, you have to make sure that the location set of the sub-choreography is a subset of the outer choreography. So and also this is this type level location set. You can think of it as a generics, right? So well, I guess the point is the location set can change when you compose choreographies. So I think yeah, I hope that answers the question.
Thanks again. I think we have time for a very quick question.
Very quick. Actually, I have two, but I will just stick to one.
You're losing time.
How much is it difficult to escape from the library. This is always something that worries me when I'm using a library. So the library imposes some restrictions, let's say, so that it works correctly.
Right.
But then, since it's a library, I can do something on the
Yes,
language.
exactly. So that is a great question, and there are a couple of ways you can get deadlocked, basically. So for example, if you use like shared mutable references with mutex in Rust, then you can get deadlocked. So our assumption is you don't use those advanced primitives, but I think it would be great if there could be something like a linter to make sure you don't accidentally use those dangerous features.
I think it's time to call the next speaker. Thanks again for the interesting talk. Okay, we have Lovro, while he set up, is going to talk about Clore, choreographic language based on Lisp, I would say. Clojure, to be precise.
Work? Test, test. Okay, nice. Good. All right. Hi, everybody. My name is Lovra. I've been working on a project called Clore together with Sung Shik for the past, let's say, 6-7 months. And today I'm going to tell you a little bit about it. I only have 20 minutes, so I'll try to give you a taste and go over the major ideas we have in this language. Sung is sadly not here today. And a small note for the reviewers that have actually looked at the Clore paper, it's completely different now, right? So everything is new, everything's changed. So just unlearn everything you know. All right, so let's start off with Clojure and Lisp. So how many of you, just a quick show of hands, how many of you have heard of Lisp? Nice. How many of you use Lisp? Boo. Okay, how many of you know about Clojure? Again, okay. So how many of you have used Clojure? Okay, okay. All right, so our idea was, so I'll say a little bit later about why Lisp and why Clojure, but our idea was to take Clojure and combine it with choreographies. We all know what this diagram is. And what do we get? We get Clore. So Clore, in a sentence, is our domain-specific language for choreographic programming embedded in Clojure. Now you can see this little prism over there. This means white light is coming in, dispersion happens. That's projection, right? Choreography comes in, disperses into its projections. All right, so now why did we choose to create a new language? So basically, Choral has core, chorus, all of these library level approaches have shown us we do want to combine choreographic languages on top of a mainstream language. Now, what I don't like is, number one, I don't want a custom toolchain. And OK, some of these approaches get rid of that. But I want more control. I want to customize the syntax. I want to have custom type checking. I want to have custom analyses. I want to do lots of custom stuff. I don't want to be constrained to the interface that the language gives me. And the only language that can give me that is, of course, Lisp, right? There's nothing else that comes close. So that's where we're going to go. So that explains sort of the first part. So basically, I need very good metaprogramming support. One other thing that I get from Lisp is the interactivity and so like a really nice fluid development cycle. And I'll showcase this a little bit later in a quick demo if I have the time. And of course, all these Lisps are usually functional programming kind of style. So that's a nice thing. Clojure specifically for a couple of reasons. Number one, there's the JVM. So Clojure is a hosted language. It sits on top of the JVM. It's a Lisp for the JVM. So we basically just steal all of the ecosystem, steal all of the interoperability. I don't need to implement any libraries. I'm happy. This concurrency support in Clojure is immaculate. It's amazing. So it's got first-class immutability, basically immutability by default everywhere. It's got high-quality persistent data structures, and this is just a natural environment for a concurrent setting such as choreographies. Finally, tooling. Of course, I would tell you just use Emacs, right? There's no other editor. But the thing is, lots of people use different tools, so we just inherit and import all of that from the existing Clojure ecosystem, as well as from the existing JVM ecosystem, right? So you have profilers, debuggers, whatever you want, you can get it. All right, so quick 1-minute Lisp crash course for those of you who are rusty. Just quickly so you can actually follow the Clore code I'll show you later. So let's go from left to right. This is a list of integers. This is a vector of characters. This is a set of keywords. Keywords are a special kind of symbol. This is a map of keywords to integers, right? Four fundamental data structures all built into Clojure as literals. Amazing. Huh? Yeah, we're now, this is not your grandfather's Lisp. Now we're in 2024. All right, here's a function definition. Notice that Clojure code is literally just a bunch of lists, right? Code is data, data is code. So this is a factorial function. Takes a single parameter n. If n is 0, you return 1. Otherwise, you multiply n by the recursive factorial of the decremented number. So quite a simple, straightforward definition. You'll notice everything is sort of compositional, very uniform, prefix notation, all that stuff. Here's a higher order lazy example. This is a lazy list of an infinite sequence of integers, and this is just going to filter the list for all numbers that are divisible by 5. And here's the cool thing about Clojure, seamless interop with Java. Any Java goop that I need to interoperate with whatever service I can find, I just do it like this, right? So this is calling a static method of the local date, and then on that object that it returns, it's calling a method getDayOfMonth. Super easy, super straightforward. Right, now we jump into Clore. And the entry point of Clore is the defcore macro. So this is a Clojure macro that we wrote. And the important part here, so that the stuff that I want to highlight is basically this macro completely expands at compile time. It's a compile time computation. And the macro basically performs projection. So unlike some of these approaches that we've heard about today that do projection at runtime, we do it completely at compile time. We're basically doing what Coral would do, but without the custom toolchain. We're just doing it by hooking into the Clojure compiler, right? So you could call this projection as a macro, if you need a catchy title. Another cool thing that we get from support for macros is that I can just reuse macros inside of Clore. All of the standard Clojure macros that I have, I can just reuse them there. So another cool thing that we have is a lightweight type system, and I'll talk about the exact types, what they are. Right now, it's not really important. Don't focus too much on the syntax. Just let your eyes glaze over just to get a feel. And then we have the kinds of expression that you can actually write in Clore. That's what comes in the body of the defcore. So basically, the ... is everything you get from Clojure. Let, do, if, whatever you want. And then these over here, 6 specific operators are Clore specific, right? And I'll explain what these are just through examples. We're not going to focus too much on very technical stuff. The reason I need a lightweight type system, right, maybe one thing I should mention, Clojure is dynamically typed, like every Lisp. And what the type system gives me, I guess this is a little bit unusual for a DSL embedded in Clojure. This is a type system that's running as part of the macro expansion, right? And it's completely just location-based. And all of the values that are still, in Clojure, they're dynamically typed. This is only telling me something about the locations, right? So I don't have an int at A. I just have a thing at A. Whatever that thing is, you decide. Another cool thing that the types allow me to do is multiply located values. So I can have choreographies as values. I can have choreographic tuples. We'll see more in a second. All right, so let's dig in. A taste of Clore. Here's a really simple choreography, no complicated behavior. To break it down, the choreography is called Simple 1. This is introducing a vector of roles. This is your current role context. You have access to A and B. Here's the signature of the top-level definition. If you're used to Haskell, this is what you would write normally, right? Top-level definition, and above it you have the signature. This means it's a choreography returning a B. Everything that would come before B would be the input parameters, which in this case there are none. So these are the value parameters. So there's the role parameters and the value parameters. In this case, what's happening, A is just going to be printing hello, and B is just going to return 1, 2, 3. Okay? So dead simple, no communications yet. Now we move on to communications. Now you can see what Fabrizio foreshadowed a little bit earlier in the day. So we're taking an X located at A, and returning a thing at B. And how do we come up with that thing at B? Well, we're moving the x from A to B. And this is the kind of cute stuff I can do when I have control over the syntax. There's no ceremony. This is literally all you need for this choreography is written here, and there's no cruft anywhere. And now we get into the sort of a little bit of a novel thing, is essentially, well, we've heard already today at least 3 or 4 times. It's actually kind of amazing that people are converging onto the same ideas. So we have the idea of replication, or I call them agreement types. So this is the double arrow, which shares knowledge about X from A to B. And now you have an agreement type where both people agree on the value of this thing. Okay? So to dig into that a little bit more, imagine you have a choreography called Maybe Inc. So the idea is to maybe we will increment an integer. Again, we have A and B. So we're taking an X. This is a small typo. There's not supposed to be an X over here. But basically, A is going to flip a coin. And depending on the outcome, it's going to share the result with B, who is then either going to increment an integer that A sends to it, or it's going to print nothing. Okay? And the cool thing about this, and I think Mako already mentioned this, is basically there's no selections, there's no merging. Knowledge of choice is basically just taken care by requiring that the guard of the conditional is an agreement type. And then all of the people involved in the agreement, in this case A and B, can participate in the branches. Otherwise, they cannot be in the branches. Another cool thing about having a completely custom sort of macro thing is that I control the error messages. So when something goes wrong, you actually get a really nice readable error message. And here I can report, if you use C over here, I would say C does not participate in the condition in the guard. Sorry, it would not be, some crazy message. Now the double arrow is really just syntax sugar for this primitive copy operator that you've seen quickly on that one slide. But not only can we share knowledge, we can also forget knowledge. And I think Maxime actually had an operator called narrow. So we are all sort of coming down to the same thing. So imagine you take an X and it's of agreement type from A to B. It's of agreement type with A and B participating, knowing about the value. You can actually forget that this X is of agreement type by using narrow. And this gives you a thing of the same value, but just located at a subset of the roles. And this is useful when I want to do, some local computation. I want to forget the agreement. I don't care about it. I'm just going to do a local thing at B. Okay? In a lot of the cases, so we have this subtyping rule that allows you to elide this explicit ugly narrowing. So a lot of the times you can just write X, and Clore is going to figure out what to do. And then what's the relationship between the double arrow and the single arrow? Well, the single arrow is just a copy followed by immediate narrow, right? Copy it over and immediately forget the sender ever had it. Okay, so that's the semantics. Okay, now we go on to lifting. So far I've used this syntax sugar. I've just explained it. Now I'm going to explain what this syntax sugar is. I call these role expressions, right? So you start, the operator is just the role from your context, and then you have a thing inside. This is really syntax sugar for an operator I called lifting. And now this is not the same as the choreographic enclaves idea. This is actually just a convenient way of informing the Clore type checker how to lift all free names and any value literals appearing in the source code, what roles to lift them to. So this is just about syntactic convenience. When I write print line nothing, I don't want to write print line at A, string at A, write it out a million times. I just want to say, within this little lexical scope, assume everything that's not annotated, just assume it's at B. Okay? So, and that's quite nice to see visually. So there's not a lot of verbosity in there. All right. This is another thing that I think Mako touched upon. So imagine, so we have our previous example with the solo increment where B was doing a solo increment on X even though it was of agreement type. Now imagine you have a function like this and you leave out the B, right? So what's going to happen now? If the above thing is syntax sugar for lifting of B, then the thing below is syntax sugar for lifting AB. And this is going to correspond to a concept that, so I call this concept a homogeneous code. This means that the inc over here is going to be interpreted as happening at both A and both B. And this is going to be an operation that will happen at both. And the assumption in CLOR is that all of these functions that happen at both, at all participants, it has to be a deterministic computation, right? So if an agreement thing comes in, an agreement thing should come out. If you violate this assumption, then stuff is going to go wrong. Usually this is not such a big problem in Clojure because we have immutability almost everywhere. Persistent data structures, all this stuff, so it's completely fine. Another feature that I want to touch upon is the idea of choreographic tuples. So a lot of the times you want a choreographic procedure that can return multiple values at different roles, right? So imagine you have an exchange key procedure, choreography, that's just implementing the Diffie-Hellman key exchange. So the implementation over here doesn't matter, it's just doing some modular exponentiation, whatever. But the important thing is that once this procedure is done, both A and B should have a key, right? And that's what I can do with a choreographic tuple. So this thing over here is really just a choreographic pair, choreographic tuple. It's saying the first slot is at A, the second, element is at B. And I introduce it with my little pack primitive. And then how do you actually use this? Well, if you have a choreography called secure, that's going to call into exchange key. And notice how we call other choreographies. We are providing the role parameters to instantiate a definition with. So one thing I forgot to mention actually is that all definitions in CLOR are location polymorphic by default, right? There are no role constants. To me, this concept doesn't even make sense, so I just go with location polymorphic everywhere. And every time you invoke another choreography, you explicitly say which role is playing which role of the target choreography. So if you do exchange key with a bunch of parameters, whatever, you get this choreographic tuple, and now you can use the unpack primitive to unpack it into two things. The first one is going to be at A, the second one's going to be at B. And then, okay, you can do some encryption in this case just with an XOR. It's completely a toy example. Okay? So that's another idea that CLOR has, the idea of these choreographic tuples for manipulating multiple return values. Another thing is forced agreement. So in the Diffie-Hellman example, actually specifically, we actually have the case where it's a mathematical result of the protocol that the key will be the same at the end, right? But you cannot capture this if the only way of transmitting shared knowledge is using copy, okay? So what we've added is this agree primitive that forces agreement. It says, here's a bunch of expressions. They all need to be at disjoint roles. And this thing is going to be of an agreement type result, okay? And if you violate the assumption that these expressions don't actually generate the same value, things are gonna go wrong. We have a bunch of little compiler options you can enable for some dynamic checks if you want. But you can decide this on a per choreography basis, which is nice. And then, so how do we rewrite now our secure definition over here to work with this new thing? Well, now it becomes simpler. Now there's nothing to unpack. You just get a K. That's your key of agreement type. Maybe I haven't mentioned it, but we also have sort of, let's say, some type inference, right? I'm not annotating what type K is. There's a type inference procedure over here that runs. Sadly, it's not as powerful as a Haskell type inference. So one of the future things I'd like to do is to do a Hindley-Milner style type inference for this thing. That would be cool. Right. One thing to say, or maybe a couple of things to say about the execution. So you've written all of these choreographies. So this thing is actually this macro, the defcore macro, is going to get expanded, blown up into multiple functions, right, for each role. So how do you actually interface with these projections from Clojure code, from standard Clojure code? How do you invoke into them? Well, you use a part of our standard, let's say, not standard library, but our runtime. You say play a role, and here you give a name of the choreography, and then something that we call a role configuration. Similar to the stuff you do in Chorus, you define like the transport, how do you send, how do you receive, Here you can basically plug in your own functions, sockets, whatever you want. UDP, TCP, doesn't even matter. It's completely transparent. And you can provide arguments for that particular projection. The way that the arguments are actually projected is just sort of an erasure style, right? So if you're mentioned in the role, you get it. If you're mentioned in the type, you get that parameter. Otherwise, you're sort of erased. That parameter disappears, kind of like in Coral. Right? And another thing that's nice that we provide is a simulator just purely for local development. So you can actually simulate the choreography locally. And what's that doing is just invoking play role behind the scenes with a bunch of little virtual threads using Java 21, which is another nice thing. All right, let's see. We have, just quickly, just to show, let's see. I'll do one example just to show how it looks. And I will choose maybe the authentication example, because I wanted to showcase the difference between this. So this is the authentication example from the book. And there's a bunch of selections and stuff going on, right? It's not easy to read. There's also like this retry thing going on. And the server has to be involved in this retry between the client and the authentication server, which kind of sucks. With our new approach, so in Clore, the way you would write this choreography would be like this. So I've separated the authentication choreography itself that involves CS and A from the agreement that the client and the authentication server are establishing. And the nice thing is that you sort of, with these agreement types, you are reifying that there is, that an agreement was established. And once you have that agreement over here, you can actually share it with S, who is then either going to send a random UID, aka the token, to the client, or the client is just going to generate an error. So now this example is very nice and modular. No selections, no merging, no nothing. Actually, before in Clore v1, this is a big rewrite, I actually did have the idea of merging and selections, and it was horrible for macros and for the type checking. It does not play nice, and this approach is much more compositional, I would say. Okay, and I think that's all I have. So feel free to ask any questions.
Yeah, I think we have. I think we have just barely time for a very quick question, and while we ask that, I would call the next speaker to get the mic and everything.
Cool. Hi, thanks for the talk. It looks to me like you can only have a process play one role at a time in a choreography, whereas in full process polymorphism, the same process can take multiple roles. Am I misunderstanding something, or do you only have that limited form?
A single role, you can invoke multiple choreographies at the same time with different, placing yourself at different positions of the instantiated choreography. So no, one process can play multiple roles at the same time.
Do you need your microphone back? I'll take it offline.
Yeah.
Okay. Also, for the sake of time, I think we should move to the next speaker. Thanks
right.
again, Lovro.
Thanks. Also, I forgot to mention, find us on GitHub and stars.
Get away. You're done.
Cool.
Okay. So, next we have Shadai that is going to talk about Suki, a choreographed distributed data flow in Rust. So, another talk about Rust and choreographies.
Okay, can everyone hear me? Yep. Cool. Yeah, so lots of Rust today in this session, so this is going to be fun. I'm Shadaj. I'm a third year, fourth year PhD student at UC Berkeley. I work on programming languages for distributed systems as part of the Hydro project. So today I'm really excited to share work on Suki, which is a new kind of approach of doing choreographed programming with the data flow approach in Rust. So a little bit of background. So I mentioned I work on the Hydro project. We're building kind of a new language stack for building distributed systems in Rust. At the core of that is this low-level language called HydroFlow, which is a streaming programming language that compiles down to really efficient Rust. HydroFlow under the hood uses a streaming actors model. I won't go into too much detail about this. If you're curious, come find me later. But we've developed this new kind of model that combines actor programming and streaming data flow programming, which gives us some nice opportunities to do optimization over declarative implementations while preserving the nice statefulness and atomic behavior of actors. Now, here's the issue. HydroFlow is a great language, but it was always designed as an IR for a higher level language stack. It was never meant to be programmed in. But we kind of built this thing, and we have other distributed systems PhDs in our research group, and we just started using it. And things kind of got out of hand, where we were starting to build actual systems in this. And we had some false starts. We said HydroFlow is bad, so we love Datalog. Half of our research group is database researchers. So we said, oh, Datalog's a nice language, so we built built this data log layer on top of HydroFlow, and it was not great. We built practice implementation and things in terms of it, but it was just a very painful experience to actually build real systems. And that's where Suki comes in. So Suki is attempt number 2 at building a nice high-level language that leverages HydroFlow but presents itself in a developer-friendly manner. So there are 3 key design goals for Suki. First, we wanted to present as a standard Rust streaming API. The lesson we learned was that developers want to use APIs in a language they're familiar with. For our group, that was Rust. And we wanted to look just like existing APIs for similar constructs in the Rust ecosystem. The second one, and this is kind of specific to the Hydro group, is we really want to support kind of doing more complex optimizations that do things like manipulate locations. So move computation between locations, delete or introduce new locations dynamically as part of the optimizations, and things like that. And I'll go into a little bit more detail on that. And lastly, the Hydro project is part of the Sky Computing Lab at Berkeley, where we're focused on multi-cloud compute. And so a big part of that is that how do you actually interact with the cloud providers where you might be deploying these choreographies to. So one of the design goals of Suki was actually kind of bring that into the programming model so you can write your choreographies and also tie them to concrete cloud resources. So Suki takes the streaming actor model that I mentioned earlier and just adds a couple more operators for networking. So now you can write your distributed data flow using traditional functional operators like map, filter, and join. But you also have an operator send, which allows you to send data over the network between 2 processes. So our locations are based on this model, and the projections that we're going to get are just across these boundaries of network. So the primary type of location that shows up in Suki is the process, which is a single actor that's going to be running at a single location. Suki also supports this concept of a cluster, which you can think of as kind of SIMD-style programming. So the idea is you have an operator like demux, which says, give me kind of an integer identifier for one of several copies. This could even be a dynamically changing cluster of machines. And each of them are going to be running a copy of the exact same data flow program. And so this allows you to handle scaling out your distributed program. Now, what makes Suki, in my opinion, really interesting is how we actually do the endpoint projection. So a lot of the discussion today, especially within the libraries section, has been on either leveraging the type system or using some runtime behavior to do your projection. Suki takes a slightly different approach where we use a concept called stage programming. So maybe quick raise of hands. Who here has heard of stage programming before? Okay, a couple of people. So stage programming is a way to kind of develop higher level library level structures that do code generation under the hood. So normally when you are writing something like in Chorus, for example, you would write your Rust program, compile it, and that's the thing you run. In Suki, there are 2 layers. So you write a Rust program using Suki, you compile it on your laptop, you run it immediately on your laptop. So no distributed programming involved. What the program does is actually spit out several Rust sources corresponding to each projection. Those you compile, and that's what you actually run. And so this gives us a lot of power to do a lot of manipulation of the data flow program before we actually project into the binaries. And it also guarantees that we have 0 overhead for the actual binaries themselves because we strip out all of the projection logic. So kind of how this materializes in Rust is, if you've seen quoting in other languages before, we developed a quoting mechanism in Rust where you can take Rust expressions, wrap it in this Q exclamation macro, and it actually does type checking of this expression. So you actually get like well-typed quoted expressions. So you preserve all the type safety while developing your program. But the way, kind of the mental model you can think under the hood is the value that this actually results in is just a string containing that expression. It is a more kind of rich AST, but you can think of it as just having a string of Rust code. You run this logic on your laptop. You're going to generate all these strings for your quoted expressions, run it through the Suki optimizer, and what will happen is these strings will just get kind of string interpolated into some generated Rust code. And those binaries are what you compile and execute. And so this allows us to do kind of all the projection locally on your developer laptop. And so again, the reason I'm kind of emphasizing this point is the code examples I'm going to show you are going to look very similar to classic choreographic programming, but they behave in very different ways. And so the programs that we're going to see now are programs that generate Rust sources. These are not the programs that are actually going to be running in the cloud. So let's take a look at some Suki code. So I'm going to use a single example to kind of walk through these 3 different design goals. Let's start by looking at kind of how this looks like to just a regular Rust developer. So when you develop a choreography with Suki, you take a couple of parameters. One is just this builder, which allows us to capture the graph that we're instantiating. But another thing you take is these things called process specs or cluster specs. So in Suki, locations are instantiated during the execution of your program on your laptop. And so you can take the specification, and that kind of allows you to instantiate several locations. And we'll see later how this ties into the provisioning of cloud resources. What's really interesting here is that the locations in a Suki program are standard Rust values. So this is in contrast to having them statically defined as types. There are some interesting trade-offs here with type safety, but here you can really just manipulate them as if they're standard in-memory values. And critically, they do not need to be statically defined, which has some interesting opportunities. So for example, if I develop a module like a subroutine that replicates state, it can just declare that, oh, I need a couple more locations, which will be where my replicas are. And so subroutines can actually just acquire additional resources as necessary. Now that we have some locations, let's start writing some programs. So in kind of a different way than traditional choreographic programming, we're focused on streaming data flow. So we're not going to write this as kind of imperative code, but instead as composition of these streaming operators. So roots in a Suki program are just a data flow node that's instantiated at a specific location. So there are a couple of different ways to instantiate this root. You can either stream some input from some external network. In this case, I'm just going to say we're going to read values out of a static Rust value. So here I have a vector just containing a single element, and we're going to stream these elements out. Note here that we quoted this vector, right? Because the actual creation of this vector that we're going to read elements out of, that needs to happen in the cloud. And so any kind of user logic that needs to be executed in the cloud needs to be wrapped in this Q exclamation mark macro to track it. Now, once you have a stream, you can send them across. This is kind of the choreography part of what we're trying to build. We have the send bin code operator, which sends data over the network. And one of the nice things we do is because we're kind of tied into the Rust type system and we know the types of elements being sent over, we can do implicit serialization. So in this case, one of the common Rust frameworks for doing binary serialization is bin code, and so we'll use that under the hood. Now that this kind of stream has been moved into a new location, we can continue processing it. So in this case, what this program actually is doing is taking an element, sending it to another location, adding one to it, sending it back. So some simple program. Again here, the Rust UDFs, these functions that are going to be transforming the data, those need to run in the cloud. So we wrap them in Q exclamation mark. And our type system actually helps guide the developer to make sure that they're quoting the right values. But kind of at the end of the day, you get this kind of straight line code that's traversing several machines and is able to do this distributed data flow. So that's kind of Suki, and I hope kind of this convinces you that we're exposing this in a way that's relatively familiar to Rust developers. Q exclamation mark is a weird thing. It takes some time for developers to get used to actually wrapping all of their functions with this. But other than this, if you're familiar with Rust, this looks a lot similar to the iterators API. So that's kind of what we're going for. The second part of Suki that I want to talk about is optimization. So this is a really core part. What I'm going to be presenting is a very dramatic simplification of 2 recent papers that we have. One which appeared at Sigmod just last month on optimizing distributed protocols, and another one from eGraphs last year. And this is kind of a combination of those techniques. So as I mentioned before, Suki, this program is running on the developer's laptop. It's not running directly in the cloud. And because we have this staged programming, this gives us an opportunity to actually build out a full IR describing our entire data flow program before we do projection. So under the hood of Suki, if you look at the implementation, we actually just build up this IR of all of the different data flow nodes we have. And they're tagged with their locations, so we know where the boundaries are. Now, one of the really cool things we can do is we can take advantage of the semantic properties of several of these operators. So for example, when you have a network involved, we can just say networks might introduce arbitrary latency. And so we can take advantage of this kind of relaxation in semantics to do some interesting optimizations. For example, instead of map running on a single process, it could instead run a cluster. We could partition the data and run it. And we know that from the perspective of the input-output observational equivalence, this program will retain its equivalence because we know that network might do whatever it wants with latency. Similarly, we can just get rid of that location entirely and fuse it together. This is the scenario where there was 0 network latency. And so by having this IR before we actually generate the projections, we're able to do a lot of these kind of dramatic optimizations. There are some gotchas. I won't go into the details about things like fault tolerance and security, but catch me afterwards if you want to talk about that. And I do want to mention that this actually works. So if you take a look at our SIGMOD paper, we showed how we're able to take an implementation of Paxos in a framework similar to this, apply a set of optimizations, and get 2.5x higher throughput purely through kind of automatic rewrites. And so we're really excited about this opportunity where you can write your program in a way where you think about things in terms of just processes. You don't even think about clusters, and we automatically figure out where a cluster or partitioning or pipelining of your distributed computation could take place and optimize your program. The last thing I want to talk about is cloud resources. So as part of the Hydra project, we also have developed the system called Hydra Deploy, which is a Rust API that allows you to easily manage cloud resources. And so one thing that I kind of glossed over earlier was this process spec, right? I mentioned that this is like a thing you need to instantiate new locations, but what does this spec actually capture? In some simple cases, it can just be something like, I would like you to spit out the Rust sources for this projection in a certain folder. But an alternative thing is you can say, hey, I want this to be a Google Cloud machine running in a specific region on a specific machine type. And that's a spec for where a location should be instantiated. And so each time I instantiate a process using the spec, that's saying I want to physically allocate a virtual machine in the cloud according to this description. What's really cool is because we're taking this choreographic approach and we know exactly where networking takes place between different locations ahead of time, when we run this on the laptop, we actually know the network topology. And so whenever we see a send, we can just map this out, and so we know the full set of cloud resources as well as the network topology between them. And one of the things we are excited about doing in the future is actually, instead of having these cloud resources being very precisely specified, like a specific region, instead you say, oh, I would like this to run on Google Cloud, or I would like to have a certain fault tolerance guarantee, and we use the network topology to derive an optimal placement of this compute. Under the hood, what this actually does is it generates a Terraform config. And so the end experience when using Suki is actually quite magical. If you write a program like this, you specify some Google Cloud, you just run the thing from your IDE, and it spins up all the machines, compiles all the Rust binaries, copies them over, and executes the program. And it actually just happens directly on your laptop. So that's a really kind of exciting feature. All right, so that's Suki, whirlwind tour of it. So in conclusion, Suki kind of presents itself as a standard Rust streaming API that's fairly familiar to developers who've used streaming data flow APIs before. But by using staged programming, we have the ability to support a wide range of optimizations that can do things like manipulate locations, instantiate new ones, and also collapse them based on these semantic relaxations. And lastly, we have the ability to actually take these choreographies and map them to physical cloud resources and have this all be part of one automated pipeline. One thing I'd like to point out is Suki is kind of a code name, but this actually is open source. So if you go to the Hydra website at hydra.run, you can go to the docs and go to HydraFlow Plus, which is a name that we need to improve for what we've been describing. And so you can actually just install the template and run, and we even include the examples for doing Google Cloud in the template. So give it a try and let us know what you think. And with that, I'd be happy to take any questions.
Thanks again. Are ready questions? Okay.
Well, first of all, what do you mean optimization? What is the metric that you like to optimize?
Yeah, this is a good question. So in our early work, it's been primarily focused on throughput in terms of things like transactions per second that you can execute. So we've been focused very much on like low-level distributed protocols. So the SIGMOD paper focuses on two-phase commit and Paxos. And so there we're just looking at how many transactions per second the cluster can support. We also have some early work on doing Byzantine fault-tolerant protocols using a similar approach.
Well, the second question is like on this fault tolerance. So I guess you are smarter enough not to restart the entire thing from scratch if only one thing fails?
Yeah, so I, again, glossed over this a bit, but when you do something like send to, because we're in this streaming format, we have the ability to let the network operator provide you with a bunch of different choices. So by default, sending says, oh, I want kind of TCP semantics. I want ordering. I want exactly once delivery. But we have the ability to customize that. So you can define a network operator that says, oh, I'm actually fine with dropping messages or reordering them. And so that allows us to kind of handle node failures and things like that.
And your tasks are independent. So do you have like assumption on the tasks that you're executing on the nodes? Final question.
So we don't assume by default that it's idempotent, but we allow users to kind of relax things, saying, oh, I'm fine with having duplicate messages. And that just impacts what the optimizer is able to do. So if you tell us more kind of weakenings of the semantics, that gives us more space of optimizations. Yeah.
Great. Are there more questions?
Super quick. I noticed that in the example, of course, there is a pattern that repeats, which is quote and send, quote and send.
Yeah.
Does that make sense to introduce like a move kind of operation so that you can cluster those?
Yeah, that's an interesting idea. Yeah, so a sugar like that where I do like a map that immediately sends to another node is a sugar you could write. The approach that we've been taking thus far is that the core API we're keeping really low level and focus on the primitive operators. And because, again, this is this library approach, you can very easily tack on your own extension APIs for whatever you want. So for example, like I showed this Demux API, but we have an extension that says broadcast, which just is sugar over taking the cross product of all your messages with the membership of your set and then just doing the normal thing under the hood.
Otherwise, it would be easier to just keep the move.
Yeah, yeah.
Yep. Okay. Cool. Thanks again for the interesting talk. And next and last, we have Gan, who's going to talk about verified library level choreographic programming with algebraic effects.
Check. Everyone hear me right? Okay, thanks for the introduction. Hi everyone, I'm Ganshen, and I'm excited to tell you about toward verified library level choreographic programming with algebraic effects. That's a pretty long title. And this is the last talk of the last session. I guess people might feel a bit overwhelmed by the so many great talks we've had so far. So as the title suggests, our paper is about doing choreographic programming with algebraic effects and proving its correctness, all in the proof assistant ACTA. But at this point, I guess people are tired and I want to, and don't want to see hundreds of ACTA code. So instead, I'm going to present a different view of our paper, which will just be choreographic programming with algebraic effects. Here's the main point I want to convey. I think algebraic effects are a viable mechanism for implementing a choreography language, and I want to advocate their use in our community. So of course, this needs a bit more explanation. So why do I think algebraic effects are a viable mechanism? There are three reasons. First, a choreography language built with algebraic effects is lightweight. The language is just a library. Unlike standalone implementations, we do not need to write a custom parser or compiler, which might require a significant amount of engineering. Second, the library implemented in this way is very concise. The code follows how we define things mathematically on paper. As the demonstration later in this talk indicates, the core functionality of a choreography language only takes less than 100 lines of code. Third, algebraic effects provide interoperability between the choreography language and the host language in which we implement it. This allows the choreography language to inherit rich ecosystems such as programming features, IDE support, and third-party libraries from the host language. A question you might want to ask now is, why algebraic effects? Especially at the end of this session, we have seen quite a few different ways to implement a library-level choreography language. So how do algebraic effects compare to them? Do algebraic effects bring anything new to the table? I think there's three reasons why I want to do this with algebraic effects. First, I think algebraic effects generalize previous library-level choreography language implementations. So two of the previous implementations that I have experience with are Haskell, which uses freer monads as its core mechanism, and Chorus, which is built on the idea of dependency injection. Having experienced both systems, I found there's something common with them. In a way, both systems define a choreography as a program with user-defined operations, and then endpoint projection gives those operation location-specific semantics. This is exactly the pattern of programming with algebraic effects. One defines uninterpreted effects and separately gives them semantics through effect handlers. Second, I think algebraic effects crystallize the core idea of library-level choreography programming. This is kind of related to the first point. Even though Haskell and Chorus share the core idea, they look very different on the surface due to the low-level details of freer monads and the dependency injection. This makes it hard for people to appreciate the core idea behind them. I think algebraic effects solve this problem by providing a simple interface to programming with effects, thus really crystallizing the core idea. Third, as a useful programming feature, algebraic effects are going mainstream as more and more languages are considering adapting them. For example, the WebAssembly community group is considering effect handlers as one of the mechanisms for supporting concurrency, asynchronous I/O, and the generators. So here we want to follow the trend and bring choreographic programming to a much broader audience. Okay, so that's some high-level points about choreographic programming with algebraic effects. Let's try to make these points a little bit more concrete. In the rest of this talk, I will demonstrate how to use OCaml, which recently added native support for effect handlers to build a library-level choreography language. Our choice of OCaml is inconsequential. The exact implementation strategy can be applied to other languages that support algebraic effects as well. And as a side note, effect handlers and algebraic effects are kind of synonyms, and I will use them interchangeably in the rest of this talk. So to begin with, let's first have a brief introduction to algebraic effects in OCaml. So algebraic effects in OCaml comprise mainly two parts: uninterpreted effects and effect handlers. Here, we are going to show an example. We will use algebraic effects to model stateful computations where we can write and read from a single storage. First, we declare the set of needed effects by extending the extensible variable type effect t from OCaml's standard library. So this effect t is defined as a generalized algebraic data type, or GADT for short. It has a type parameter denoted by the underscore, and each constructor is allowed to instantiate to a different type. We extend effect t with two new constructors, get and put. The declaration says the get effect takes no argument and returns an integer, and the put effect takes an integer argument and returns a unit. With the effect declaration, we can write some computations that perform those effects. Here's a function that reads the integer from the storage, writes back it times 2, we read the storage and print out the result. Next, we can write an effect handler that handles effects performed by a computation. We will handle a stateful computation as a state transforming function, the standard functional interpretation. An effect handler in OCaml is a record with 3 fields, a return case for handling pure values returned from the computation, an exception case for handling exceptions raised from the computation, and the most important part, an effect case for handling effects. Let's take a close look at the effect case. It is a function taking in an effect and returning an optional handling clause. Here we are saying that we will handle the get and the put effect and ignore others. For each effect, the handling clause is provided with a continuation k, which represents the remaining program after the effect is handled. For the get effect, we continue with the state from the context and execute the remaining computation with the same state. Similarly, for the put effect, we continue with a unit and execute the remaining program with the new state. We don't need to read all of this in detail. Here, I'm just trying to give you a feeling of what programming with effect handler is like. So finally, we use the match-with function to put everything together. The match-with function runs a computation. When the effect is performed, it captures the remaining program as a continuation, jumps out of it to the effect handler, and execute the corresponding handling clause supplied with the continuation. In a way, effect handlers can be seen as a generalization of exception handlers. Similar to exception handlers, they allow control flow to jump out of the current execution context. Unlike exception handlers, effect handlers are also provided with a continuation, allowing them to return to where they left off. So this concludes the set of APIs one needs to know to use algebraic effects in OCaml. Now let's move on to see how to implement a choreography language with this feature. The first thing we need to figure out is the effect that a choreography can have. The most fundamental effect, obviously, is com, which describes an instance of communication between two locations. So here, we extend effect.t with a new constructor com. The com constructor takes two locations representing the sender and the receiver, respectively, a message of arbitrary type A marked as lazy, and returns a located value of type A. So here, loc is our location type. It can be as simple as plain strings or anything with decidable equality. The message is marked as lazy by using the lazy t type from OCaml to delay its evaluation. Because OCaml is an eager language, all arguments are evaluated before a function or constructor is called. Making message lazy allows the endpoint projection to selectively evaluate them as needed, which we will see in a moment. We could also have achieved the same thing by wrapping the message in a dummy function, but using the lazy t type makes the intention much more explicit. The com effect returns a located value of type A. So what are they? A located value represents a value at a specific location. It is similar to an optional value. It is either present with a value of type A or absent. Within a choreography, we have the implicit guarantee that a located value is always present for the receiver of com. Otherwise, it is absent. We provide an unwrap function to extract the value from a present located value and raise an exception if it's absent. Note that it's the programmer's responsibility to ensure a choreography only calls unwrap on a present located value. In a typical choreography language, we would like to enforce this statically using a type system or similar techniques. However, here, for simplicity, we leave that out. Next, we define two helper functions for performing the com effect. The locally function executes a piece of code locally. It is defined as performing the com effect with the sender and receiver being the same. The com function is just a thing wrapper to the uppercase com constructor. Now we can write some choreographies with the functions we have defined. Here is a distributed double function that involves two locations, Alice and Bob. First, Alice sends an integer they read from the standard input to Bob. Then Bob unwraps the integer, times it by 2, and sends the result back to Alice. Finally, Alice unwraps the result and prints it out. Here, we use the lazy keyword to create a lazy value. The expression following the lazy keyword is not evaluated immediately. I want to highlight how much this looks like a choreography we define on paper. Here's a choreography excerpt from a recently published paper. I think it's actually Pirouette. You can see that the two programs share a very similar structure, minus some syntactic differences. On paper, we tend to write variable bindings on the right side, and com is defined as an infix operator. OK, so our next job is to figure out how to define endpoint projection as effect handlers. So first, we will assume that there's a pair of functions send and receive for sending and receiving messages among locations. The exact implementation is irrelevant to our exposition. Next, we define the endpoint projection function EPP. EPP takes a choreography C and the location L, and the function body is a call to the matchWith function on C with an effect handler specific for L. For the return case, we simply return the result, and for the exception case, we propagate the exception to the outside. The most interesting part is the effect case. Let's take a close look at them. So there's only one effect we need to deal with, the com effect. Here, we are supplied with the sender and receiver locations, a delayed message, and the continuation K. If the target location is equal to the sender and the receiver, we handle this effect as a local computation. We evaluate the delayed message using the force function from OCaml and continue the rest of the program with the result. If the target location is equal to the sender, we handle this as a send. We send the forced message and continue with the absent located value. If the target location is only equal to the receiver, we handle this effect as a receive. We call the receive function, get a result, and continue the rest of the program with that. Finally, if the target location is not equal to either the sender or the receiver, we handle this effect as a no op. We continue the rest of the program with absent located value. Now we can execute the distributed double program like this. Okay, so far so good. Looks pretty simple, right? But there's an elephant in the room. What about conditionals? As people here know, conditionals are notoriously hard in choreographic programming because nodes need to be informed of the choice to decide what to do next. And we want to do this correctly and efficiently. In other words, inform and only inform nodes that need to know the choice. And also, we want to put the least burden on programmers in terms of annotations they have to write. Achieving the perfect balance between these three is not easy, and there's ongoing work on this, and we've heard a lot today. Here, I want to show algebraic effects enable fast prototyping by implementing recently proposed announce enclave-based conditionals using algebraic effects. So the choreography language we have implemented so far actually already support conditionals, but in a limited form. We can use OCaml's if then else, and everything seems to work if we don't branch on a located value. But things will go wrong if we try to branch on a located value, as it might not be present at all locations. So we can fix this by adding two new effects to our language, announce and enclave. Announce broadcasts a choice to a set of locations, so they can all branch on that. But some locations don't need to know the choice. They do not participate in any of the branches, or their behavior are not altered by the choice. So we introduce another effect, enclave, that carves out a sub-choreography and only execute it for a set of locations. With this design recipe in mind, we extend our effect with two new constructors. The announce effect is almost the same as com effect, except the receiver now can be a set of locations. The enclave effect takes a list of locations who will execute the sub-choreography. A sub-choreography returns some value of type A and returns a located value of type A. The endpoint projection for announce is, again, almost the same as com, except now we are dealing with a list of receivers. So if we are the sender, we need to iterate the send over the receiver list. The endpoint projection for enclave is also straightforward. If the target location is one of the locations participating in the enclave, we recursively call EPP on the sub-choreography and continue with the result of it. Otherwise, we continue with an absent located value. Of course, there's more improvements we can make here. For example, our implementation only allows a single location to announce the choice. But in practice, we might want to announce the choice transitively through multiple locations to take advantage of the network topology. We believe it's also doable with algebraic effects by introducing more effects. Here, the point is not to show a perfect way of doing conditionals, but to show algebraic effects enable fast and easy prototyping. So now we have reached the end of this talk. I'd like to discuss several things we are considering doing next. First, we want to keep growing the language, adding new features, and see if algebraic effects are up for the task. Second, we want to formalize this idea of choreographic programming with algebraic effects and prove its correctness, namely deadlock freedom. Most of the existing formalization is for standalone choreography languages. Although there are some similarities between a standalone and a library level choreography language, there are also some noticeable differences. For one thing, our library level language has this notion of located values that's defined like an optional value. And it's critical for the correctness proof that they are used rightly. So it's worth developing a new formalization. Our paper contains an initial attempt at formalizing some of the ideas here in ACTA, but there are still some ongoing parts. Last, we want to bring this idea of implementing choreographic programming to more languages with native support of algebraic effects. Thank you.
thanks for the talk. Are there any questions? Jacopo, I'm going to let you in the queue for once.
So the COM effect you talked about, it has this lazy component.
Mhm.
So that's essentially a thunk.
Yes.
Can that? It looked like from the code that it can't, but I was wondering, can that itself do another communication when you run the lazy computation?
Right now, it can't.
So it would just be unhandled if it did.
Yes. Yeah. When we force the message, when we do the forcing, it's not provided with effect handler. So if you try to do COM inside it, it's unhandled basically. Yeah. So
is that the behavior you want? I guess it may well be. But
yeah. Right now, I don't find like an application where I have to do another like a hierarchical choreography like here. No need here.
Well, one question is about performances. Do you think that by using effect handlers in a way we can reach performances of other languages?
It depends on how effect handlers are implemented in that language. So for OCaml, one thing I can tell is the performance is very good. It's almost as good as just calling the function directly. But there's some OCaml achieved this because because they constrain the way you use continuations. The continuation can be only used once, so they can sort of have some very efficient representation of continuation. But for languages where you want to use continuations more than one times, the performance might not be as good as a more direct implementation.
And that's an open question. Have you thought if these effect handlers can in a way be one of the ways to have fault tolerance for choreography? So if messages fails or things like this, can they be one of the ingredients to solve this issue?
So the question is how to deal with failures. So one way to deal with that is extend the type of COM to not returning a located value, but to returning a maybe located value with the nothing optional located value, with the non-case being that something bad has happened. I guess that's one way to do that.
So this is all in OCaml. You mentioned that you had an earlier Agda-based system that you'd started on. Do you anticipate a machine? And I guess you've also mentioned that there are various things that aren't checked by the type system right now.
Yes.
Do you expect a machine proof of correctness in this system?
Yes. In our Agda formalization, we actually have more fancier types. So located value are annotated with their location.
So this is not supplanting the Agda. This is in place of for today.
Yeah, I would say they are in parallel. The Agda is more theoretic focused. This one is more practical. So I don't want to. I could have do some type level tricks to type located value more precisely, but I figured just to make it simple and people understand. Yeah, so I left that one.
Okay. There are no more questions. Then we can thank the speaker again. And if I can borrow 5 more minutes of your time, we have some closing remarks. Okay, so all good things must come to an end, unfortunately. This was the last talk of the last session. In general, I think it was a very interesting day in terms of, what's happening here? Disappear. In terms of talks and topics and chats with everybody, our main objective in organizing this workshop was getting people together. As we've seen, there are many different groups working on this topic. Come on. Just a reminder, we're going for dinner at Bruins. In 20 minutes, we're leaving from here. There is a link on the conference website with directions, how to get there, and everything. And just remember that the kitchen closes at 8:30. Good. One last thing, we're organizing an impromptu business meeting tomorrow. It starts at 10:30 here at the director rooms. Otherwise, if you want to join online, we're setting up a Zoom session. Just send a link, an email to any of the chairs, and we'll reply with a link. We have the room until 12:20. I don't expect it will take that long. But the main objective, or at least the tentative agenda, is to discuss what happens next. What happens after these workshops? How do we go on building this community, engaging everybody? Essentially, what are the next steps? What happens after this? There are other things we would like to discuss, like try to map all the efforts that has been done in the community in terms of projects, tools. Well, maybe publication is too ambitious for tomorrow, but at least have an idea of how to go about this. And yeah, essentially discussing what happens after this. So, thanks again. Sorry, Fabrizio. Let me run that.
Does this work? Oh. Before you finish, I just wanted to suggest a big applause for Lindsay, Marco, and Saverio for organizing this. It's been amazing.
Thanks. Well, also thanks to everybody that attended, everybody that submitted.
Let's have a round of applause, one last round of applause for all of our speakers.
Yes. And our PC that help with the reviews, because there is also that task. And last but not least, PLDI for helping us with the organization and hosting us. Good. Thank you, everybody.